Which of the following is not a hyperparameter of the scikit-learn logistic regression model? The question asks about a hyperparameter that is not part of the scikit-learn logistic regression model. A. Penalty. The penalty hyperparameter is used to control the type of regularization applied in a logistic regression model. It can be set to L1 for L1 regularization, L2 for L2 regularization, or elastic net for a combination of both. B. C. The C hyperparameter controls the inverse of the regularization strength. A smaller value of C corresponds to stronger regularization, which can help prevent overfitting. C. Solver. The solver hyperparameter determines the optimization algorithm used to find the optimal values for the model's parameters. Possible values include LBFGS, Newton CG, liblinear, SAG, and Saga. D. All of the above. All the options penalty, C, and solver are indeed hyperparameters of the logistic regression model in scikit-learn. D. All of the above. The diagram clearly states that all the provided choices are hyperparameters of a logistic regression model. So, the correct answer is D. All of the above. Parameters that are set before training a model. Hyperparameters are settings that define the overall structure and behavior of a machine learning model. They are not learned during training, but rather chosen by the user or data scientist before the training process begins. Common examples of hyperparameters include the learning rate in gradient descent, the number of hidden layers in a neural network, and the regularization strength in a linear model. Technique to prevent overfitting by adding a penalty term to the loss function. Regularization is a technique used to prevent overfitting in machine learning models. It works by adding a penalty term to the loss function that discourages the model from learning overly complex patterns in the training data. The idea is that by adding this penalty, the model is forced to find simpler solutions that generalize better to unseen data. Common types of regularization include L1 regularization lasso, L2 regularization ridge, and elastic net regularization. In the context of the logistic regression model, the penalty hyperparameter controls the type of regularization applied. Method used to find the optimal values for the model's parameters. An optimization algorithm is a mathematical procedure used to find the best set of parameters for a machine learning model. The goal is to minimize the loss function, which measures how well the model fits the training data. There are various optimization algorithms available, each with its strengths and weaknesses. The solver hyperparameter in the logistic regression model allows you to choose the optimization algorithm that you believe will perform best for your specific problem. Credit risk assessment. Logistic regression is widely used in credit risk assessment to predict the likelihood of a borrower defaulting on a loan. The model can take into account various factors like credit history, income, employment status, and debt-to-income ratio to estimate the risk. Fraud detection. Fraud detection is another common application of logistic regression. It can help identify potentially fraudulent transactions by analyzing patterns in data such as purchase amounts, transaction history, and location information. Medical diagnosis. Logistic regression can be used in medical diagnosis to predict the likelihood of a patient having a particular disease based on their symptoms, medical history, and test results. Sentiment analysis. Sentiment analysis involves classifying text data as positive, negative, or neutral. Logistic regression can be used to build sentiment classifiers by analyzing features like a presence of specific words or phrases. Email spam filtering. Logistic regression is frequently used to build spam filters that can classify emails as spam or legitimate. The model learns from a training dataset of labeled emails to identify patterns associated with spam emails. Which of the following statements accurately describes the role of cross-validation in logistic regression CV from sklearn? A. It optimizes the hyperparameter C regularization strength by dividing the training data into K folds and evaluating the model's performance on each fold. B. It helps prevent overfitting by splitting the data into training and testing sets and evaluating the model on the testing set. C. It automatically selects the best number of features for the logistic regression model using feature importance scores. D. It performs a grid search over a range of regularization strengths and solver algorithms to find the optimal combination. True. This statement accurately describes the role of cross-validation in logistic regression CV. The class uses cross-validation to find the best value for the regularization strength. Hyperparameter C. The data is divided into K folds, and the model is trained on K1 folds while evaluating its performance on the remaining fold. This process is repeated for each fold, and the average performance across all folds is used to select the best C value. False. While cross-validation helps prevent overfitting, it doesn't do it by splitting the data into training and testing sets in the way described. Instead, it splits the data into multiple folds and trains the model on a subset of folds while evaluating it on the remaining folds. This process is repeated for different folds to get a more robust estimate of the model's performance. False. This is incorrect. Cross-validation in logistic regression CV is specifically focused on hyperparameter optimization, particularly the regularization strength C. Feature selection is a separate process that can be achieved using techniques like feature importance scores or feature selection algorithms. False. While logistic regression CV can perform a grid search to find the best C value, it doesn't search over solver algorithms. The solver algorithm is usually specified by the user. Logistic regression CV primarily focuses on optimizing the regularization strength C using cross-validation. A. Logistic regression. A statistical model used for binary classification problems. It predicts the probability of an instance belonging to a specific class, predicting customer churn, identifying customers likely to cancel their subscriptions based on their usage patterns and demographic data. Fraud detection, detecting fraudulent transactions in financial systems by analyzing transaction history and user behavior. Medical diagnosis, assisting in classifying medical conditions based on patient symptoms and test results. Suppose we have a dataset of customer information with features like age, income, and tenure, subscription duration. We want to predict whether a customer will churn, cancel their subscription or not. Logistic regression can be used to build a model that takes these features as input and outputs a probability of churn. Cross-validation. A technique used to evaluate the performance of a model on unseen data by dividing the data into multiple folds, training on some folds, and testing on the remaining folds. Model selection, choosing the best model from a set of candidate models by comparing their performance on cross-validation. Hyperparameter tuning, finding the optimal values for model parameters that are not learned during training, such as regularization strength. Performance evaluation, estimating the generalization error of a model on unseen data. Imagine we want to build a model to predict house prices. We can use cross-validation to evaluate the performance of different regression models, e.g., Linear regression. Decision tree regression on the same dataset. We can divide the data into 5 folds and train each model on 4 folds while testing on the remaining fold. By averaging the performance across all folds, we can get a more reliable estimate of the model's performance. Hyperparameter optimization. The process of finding the optimal values for parameters that are not learned during model training. E.g., regularization strength, number of hidden layers in a neural network. Improving model performance. Optimizing hyperparameters can significantly improve the performance of a model. Preventing overfitting using cross-validation during hyperparameter optimization helps to prevent overfitting. Finding the best model configuration. Searching for the optimal combination of hyperparameters allows you to find the best model configuration for your specific problem. Suppose we are training a support vector machine (SVM) model for image classification. The hyperparameters of an SVM include the regularization strength C and the kernel function. We can use grid search with cross-validation to find the optimal values for these hyperparameters. By evaluating the model's performance on different combinations of C and kernel functions, we can find the combination that yields the best performance. Which of the following statements are true about the passive-aggressive classifier in scikit-learn? A. It is suitable for online learning. B. It is a linear model that updates its weights based on misclassifications. C. It is robust to outliers and noisy data. D. It is generally used for multi-class classification tasks. E. All of the above. Correct. The passive-aggressive classifier is indeed suitable for online learning because it updates its model weights based on each new data point as it arrives. This makes it efficient for processing large datasets sequentially. Online learning. Correct. The passive-aggressive classifier is a linear model, meaning it uses a linear function to make predictions. The weights of this linear function are adjusted based on misclassifications, where the model makes a wrong prediction. The algorithm aggressively updates the weights to correct these errors. Linear model. Correct. The passive-aggressive classifier is known for its robustness to outliers and noisy data. It is designed to handle data points that deviate significantly from the general trend, making it suitable for real-world scenarios where data quality may not be perfect. Robust to outliers and noisy data. Correct. While commonly used for binary classification to classes, the passive-aggressive classifier can also handle multi-class classification tasks. This means it can classify data into multiple categories, such as different types of animals in an image classification task. Multi-class classification. Correct. As all the statements A, B, C, and D are true, the correct answer is E. All of the above. Passive-aggressive classifier. E. All of the above. Online learning. A type of machine learning where the model is trained on data that arrives sequentially, and the model updates its parameters based on each new data point. Spam detection. The spam filter can be trained on new emails as they arrive, updating its model to identify new spam patterns effectively. Imagine an email spam detection model. It can be trained on a small dataset of emails initially. As new emails arrive, the model updates its spam detection rules based on the newly classified emails. This ensures that the model stays up to date and can identify new spam patterns. Linear model. A machine learning model that uses a linear function to predict the target variable. It assumes that the relationship between the input features and the target variable is linear. Predicting house prices. A linear model can be used to predict house prices based on features such as size, location, and number of bedrooms. Consider predicting house prices. A linear model might use features like square footage, number of bedrooms, and distance from the city center. The model learns a linear relationship between these features and the house price. For example, y200 by 1100 x2 to 50 x3, where y is the house price, x1 is square footage, x2 is the number of bedrooms, and x3 is the distance from the city center. Robust to outliers and noisy data. The model is designed to handle data points that are significantly different from the rest of data. It can still learn effectively in the presence of noisy data, making it suitable for real-world applications where data quality may not be perfect. Fraud detection. A robust model is crucial in fraud detection, as fraudulent transactions often exhibit unusual patterns compared to legitimate ones. Think about credit card fraud detection. The model should be able to identify fraudulent transactions even if they are unusual. For instance, a transaction for a large amount in a foreign country might be flagged as potentially fraudulent. A robust model can still learn from this data without being heavily influenced by the outlier. Transaction. Multi-class classification. A classification task where the target variable can take on more than two values. For example, classifying images into different types of animals. Image classification. A multi-class classification model can be trained to classify images into different categories, such as cats, dogs, or birds. Let's say you want to classify images of animals. A multi-class classification model could be trained to identify different types of animals, such as cats, dogs, birds, and horses. The model would learn to distinguish between these categories based on features in the images, like shapes, textures, and colors. Which of the following statements is true about the perceptron algorithm in sklearn? sklearn, linear model, perceptron. A. It can only handle linearly separable datasets. B. It utilizes a nonlinear activation function. C. It inherently handles multi-class classification. D. It implements stochastic gradient descent for training. E. All of the above. A. It can only handle linearly separable datasets, while the perceptron is best suited for linearly separable data. In practice, it can often converge to a reasonable solution even on datasets with some degree of overlap. It might not perfectly classify all data points but can learn a decision boundary that minimizes errors. False. B. It utilizes a nonlinear activation function. The perceptron uses a linear activation function, which is the identity function. This means the output is simply the weighted sum of the inputs. False. C. It inherently handles multi-class classification. The perceptron in sklearn is designed for binary classification, meaning it distinguishes between two classes. For multi-class problems, you would typically need to employ techniques like 1 vs rest or 1 vs 1. False. D. It implements stochastic gradient descent for training. The perceptron algorithm, in its simplest form, uses an iterative update rule based on misclassified samples, while stochastic gradient descent is often used in machine learning. The perceptron's training process is not strictly considered stochastic gradient descent. False. E. All of the above. The perceptron algorithm in sklearn possesses the characteristics listed in all the choices. It primarily works with linearly separable data but can handle some degree of overlap. Utilizes a linear activation function. Is designed for binary classification, and does not strictly implement stochastic gradient descent. While it's not ideal for highly complex datasets or multi-class scenarios, it serves as a foundational algorithm in machine learning. True. A. A dataset is linearly separable if a straight line or hyperplane in higher dimensions can be drawn. To perfectly separate the data points belonging to different classes, the perceptron works best on such datasets. Imagine classifying emails as spam or not spam. If the words free, money, and urgent are highly indicative of spam, we can draw a line separating emails with these words from those without, making the dataset linearly separable. An activation function determines the output of a neuron based on its weighted sum of inputs. The perceptron uses a linear activation function, which is the identity function output-input. This contrasts with nonlinear activation functions commonly used in deep learning. Suppose a neuron receives inputs x12 and x23 with weights w11 and w2 0.5. The weighted sum is 2.1, 5 3.5. With a linear activation function, the output is also 3.5. Nonlinear functions, like sigmoid or ReLU, would introduce a transformation to this value. Binary classification refers to a task where you want to predict one of two possible outcomes. The perceptron is specifically designed for this type of classification problem. Classifying images as cat or dog is a binary classification task. We want to predict whether an image belongs to one class or the other. SGD is a widely used optimization algorithm in machine learning. It iteratively updates model parameters by considering small batches of data. The perceptron, in its basic form, does not use SGD, but rather updates based on individual misclassified samples. In SGD, we randomly select a small subset of data a batch and update the model's parameters based on a error observed in this batch. The perceptron, however, looks at each misclassified sample individually and updates the weights to correct the error. Multi-class classification involves predicting more than two classes. The perceptron is not directly suited for multi-class problems. Classifying images as cat, dog, bird, or fish is a multi-class problem. We need to predict which of these four classes an image belongs to. Which of the following statements accurately describes the rich classifier in sklearn? A. It is a linear model that adds L2 regularization to the loss function to prevent overfitting. B. It uses a sigmoid function to predict class probabilities. C. It is primarily used for binary classification tasks. D. All of the above. True. Rich classifier, being a linear model, utilizes L2 regularization to control the magnitude of coefficients during the training process. This regularization technique helps prevent overfitting by shrinking the coefficients towards zero, effectively simplifying the model and improving its generalization to unseen data. L2 regularization. Imagine you are building a model to predict house prices based on features like square footage, number of bedrooms, and location. Overfitting occurs when the model becomes too complex and learns the training data too well, potentially leading to poor predictions on new houses. L2 regularization helps prevent this by penalizing large coefficient values, making the model more robust to noise in the data. True. The rich classifier employs a sigmoid function to produce predictions. This function transforms a linear combination of features into a value between 0 and 1, representing the probability of belonging to a particular class. This makes it suitable for multi-class classification tasks as it can handle more than two classes. Sigmoid function. Consider classifying emails as spam or not spam. The sigmoid function helps convert the output of the linear model a score into a probability score, indicating the likelihood of an email being classified as spam. A higher probability closer to 1 indicates a stronger spam classification. True. While rich classifier is capable of handling multi-class classification problems, it's often employed for binary classification tasks, where the goal is to distinguish between two classes. This is due to its simplicity and effectiveness in solving such problems. Binary classification. Think about credit risk assessment where you aim to classify applicants as low risk or high risk borrowers. Rich classifier can efficiently handle this task by separating the data into two classes based on features like credit history, income, and debt-to-income ratio. True, since statements A, B, and C are all accurate descriptions of the rich classifier in sklearn. The correct answer is all of the above. Rich classifier. Rich classifier finds application in various domains like finance, healthcare, and marketing. For instance, in marketing, it can help predict customer behavior based on their purchase history, demographics, and browsing patterns, enabling targeted advertising campaigns. D. All of the above. Let's consider a simple example where we want to predict whether a student will pass or fail a test based on their scores in two subjects, math and science. We have a dataset of 5 students with their scores and whether they passed or failed: 1 for pass, 0 for fail, 70, 85, 60, 90, 75, 80, 75, 65, 95, 85, 1, 1, 0, 1, 1. Using the rich classifier with L2 regularization, we train a model to find the optimal coefficients for the linear equation that predicts the probability of passing the test based on the math and science scores. The model learns to assign weights to each subject score, penalizing large coefficients to prevent overfitting. These weights are then used to predict the probability of passing for new students. The trained model can then be used to predict the probability of passing for a new student with scores of, say, 80 in math and 70 in science. The model will use the learned coefficients to compute a weighted sum of the scores and then apply the sigmoid function to produce a probability score between 0 and 1, indicating the likelihood of this student passing the test. Which of the following statements accurately describes the rich classifier CV estimator in sklearn? A. Rich classifier CV is a linear classifier that utilizes L2 regularization and performs cross-validation to select the optimal regularization strength. B. Rich classifier CV implements a nonlinear decision boundary, making it suitable for complex datasets. C. Rich classifier CV employs a tree-based approach for classification, similar to random forests. D. Rich classifier CV is designed specifically for multi-class classification tasks, handling multiple output classes. A. True. Correct. This statement accurately captures the essence of rich classifier CV. It is indeed a linear classifier, meaning it seeks to find a linear decision boundary to separate classes. It uses L2 regularization, which penalizes large coefficient values to prevent overfitting and enhance generalization. The CV in its name stands for cross-validation, indicating that the model automatically performs cross-validation to find the optimal value of a regularization parameter alpha. Linear classifier. Rich classifier CV operates on a linear decision boundary, making it effective for problems where the relationship between features and the target variable is primarily linear. L2 regularization. This technique helps prevent overfitting by penalizing large coefficient values. This improves the model's generalization ability and robustness to noisy data. Cross-validation. Rich classifier CV automatically performs cross-validation to determine the optimal value of a Regularization parameter alpha. This ensures the model is well suited to the data and generalizes well to unseen data. False. Incorrect. Rich classifier CV is a linear classifier, meaning its decision boundary is linear. It's not suitable for complex datasets with nonlinear relationships between features and the target variable. For those scenarios, models like support vector machines with nonlinear kernels or decision tree-based methods would be more appropriate. Linear classifier. Rich classifier CV operates on a linear decision boundary, making it effective for problems where the relationship between features and the target variable is primarily linear. False. Incorrect. Rich classifier CV is not based on a tree-based approach like random forests. It uses a linear model with L2 regularization and cross-validation, making it distinct from ensemble methods like random forests. Linear classifier. Rich classifier CV operates on a linear decision boundary, making it effective for problems where the relationship between features and the target variable is primarily linear. L2 regularization. This technique helps prevent overfitting by penalizing large coefficient values. This improves the model's generalization ability and robustness to noisy data. Cross-validation. Rich classifier CV automatically performs cross-validation to determine the optimal value of a regularization parameter alpha. This ensures the model is well suited to the data and generalizes well to unseen data. False. Incorrect. While rich classifier CV can handle multi-class classification tasks, it is not specifically designed for them. Both binary and multi-class classification problems can be addressed by this model. Linear classifier. Rich classifier CV operates on a linear decision boundary, making it effective for problems where the relationship between features and the target variable is primarily linear. Linear regression. Ridge regression. L2 regularization. Cross-validation. Overfitting. Generalization. Regularization parameter alpha. Spam detection. Customer churn prediction. Medical diagnosis. Fraud detection. Image classification. You have a dataset with highly correlated features and a complex multi-class classification problem. Which of the following techniques would be most appropriate for addressing potential overfitting and selecting an optimal regularization parameter for a rich classifier model? A. K-fold cross-validation. B. Grid search CV. C. Rich classifier CV. D. All of the above. K-fold cross-validation helps prevent overfitting by evaluating a model's performance on unseen data, providing a more realistic estimate of its generalizability. While it doesn't directly select the optimal regularization parameter, it helps assess how well a model with a chosen alpha performs. K-fold cross-validation. Grid search CV systematically explores a range of hyperparameter values, including the regularization parameter alpha in a rich classifier. It uses cross-validation to evaluate the model's performance for each hyperparameter combination, identifying the optimal one. Grid search CV. Rich classifier CV is designed specifically to find the optimal regularization parameter alpha for a rich classifier model. It uses cross-validation to find the alpha value that minimizes the error on unseen data, directly addressing overfitting. Rich classifier CV. All of the options contribute to a robust and effective approach to building a rich classifier model with optimized regularization. K-fold cross-validation helps assess the model's generalizability. Grid search CV helps find the best hyperparameters. And rich classifier CV automatically finds the optimal regularization strength. All of the above. D. All of the above. Combines rich classifier with built-in cross-validation for finding the optimal alpha. Regularization strength. When you need a rich classifier model with automatic alpha selection and reduced overfitting. Splits the data into k folds. Trains on k1 folds. And tests on the remaining fold. Repeats this process for each fold to get an average performance metric. Estimating a model's generalizability, how well it performs on unseen data, and helping to prevent overfitting. Exhaustively searches through a predefined grid of hyperparameters like alpha in rich classifier. Using cross-validation to find the best combination. Finding the best model hyperparameters when you want to optimize performance across various settings. A technique used to prevent overfitting by adding a penalty to the model's complexity. Ridge regression adds a penalty proportional to the squared magnitude of the coefficients. In datasets with high correlation among features multicollinearity, regularization helps to stabilize the model and prevent it from becoming too sensitive to small changes in the data. A situation where a model learns the training data too well, becoming overly sensitive to noise and performing poorly on unseen data. When a model is overfitting, its predictions are not generalizable to new data. It's crucial to use techniques like regularization and cross-validation to address overfitting. Parameters of a machine learning model that are not learned from the data but are set before training. Examples include alpha in rich classifier and k in k-fold cross-validation. Properly tuning hyperparameters is crucial for achieving optimal performance. Techniques like grid search CV help us find the best hyperparameter values. Which of the following are core capabilities of sklearn's SGD classifier? A. Efficient handling of large datasets. B. Ability to learn from sparse data. C. Support for various loss functions. D. All of the above. This statement is correct. SGD classifier utilizes stochastic gradient descent (SGD), an optimization algorithm that updates model parameters iteratively using small batches of data. This batch processing approach makes it highly efficient for handling large datasets as it reduces the computational demands compared to batch gradient descent algorithms that process the entire dataset at once. Efficient handling of large datasets. SGD classifier's ability to process data in batches. Stochastic gradient descent makes it highly efficient for large datasets. It updates the model with a small subset of the data at each iteration, making it computationally less demanding than batch gradient descent algorithms. This statement is correct. SGD classifier is adept at handling sparse data, which is characterized by many zero values. This capability is crucial in scenarios where features have high dimensionality, commonly encountered in text analysis and image processing. Ability to learn from sparse data. SGD classifier can handle data with many zero values sparse data effectively. This is particularly useful in scenarios where features have high dimensionality, such as text analysis or image processing. This statement is correct. SGD classifier provides flexibility by allowing you to choose different loss functions like hinge, log, and modified Huber, tailored to the specific type of classification problem you are addressing. Support for various loss functions. SGD classifier provides flexibility by allowing you to choose different loss functions hinge, log, modified Huber that are tailored to the specific type of classification problem you are addressing. This statement is correct. Since options A, B, and C are all true, the statement all of the above is also correct. D. All of the above. D. All of the above. An optimization algorithm that updates model parameters iteratively using small batches of data. It's often preferred for large datasets as it's computationally more efficient than batch gradient descent. Imagine training a model to predict house prices. With SGD, you might train the model on a batch of 100 houses at a time, updating the model parameters based on those 100 samples. You repeat this process with different batches until the model converges. A mathematical function that measures the error between the predicted and actual values. The goal of a machine learning model is to minimize this error. And the loss function guides the model's learning process by providing a measure of how well it's performing. Consider a simple linear regression model predicting house prices. The mean squared error MSE is a common loss function. It calculates the average squared difference between the predicted and actual house prices, providing a measure of the model's prediction error. Data with many zero values, commonly found in high-dimensional feature spaces like text or image data where many features are not relevant to the prediction task. Suppose you are building a model to analyze customer reviews. Each review can be represented as a vector of words features. However, most reviews won't contain all possible words. This creates a sparse data representation where many words features have zero values. An optimization algorithm that uses the entire training dataset to update model parameters in each iteration. While accurate, it can be computationally expensive for large datasets. In a house price prediction scenario, batch gradient descent would use the entire dataset of houses to update the model parameters in each iteration. This can be slow if the dataset is massive. You are working on a fraud detection system using the SGD1 class SVM model from sklearn. Which of the following statements is true about this model's application in this context? A. SGD1 class SVM is best suited for detecting outliers in high-dimensional datasets with sparse features. B. The model assumes a Gaussian distribution of data points, making it ideal for nonlinear outlier detection. C. SGD1 class SVM effectively handles both linear and nonlinear outlier detection tasks. D. All of the above. This statement is true. SGD1 class SVM excels in handling high-dimensional datasets with sparse features, which are common in fraud detection scenarios. These datasets typically have a large number of features, many of which have zero values. SGD1 class SVM's ability to efficiently manage sparsity makes it a powerful tool for outlier detection in such contexts. High-dimensional datasets, sparse features. This statement is false. SGD1 class SVM does not assume a Gaussian distribution of data points. It's a non-parametric method, meaning it doesn't make assumptions about the underlying data distribution. This makes it more flexible and suitable for handling complex, nonlinear outlier patterns, which are often encountered in real-world fraud detection. 1 class SVM. This statement is true. SGD1 class SVM can handle both linear and nonlinear outlier detection tasks effectively. It uses kernel functions to transform the data into a higher dimensional space. This allows it to create nonlinear decision boundaries, enabling the identification of complex outlier patterns that wouldn't be captured by linear models. This flexibility makes it well suited for fraud detection, where outlier patterns can be quite intricate. Kernel functions. This statement is true, given that statements A and C are true, and statement B is false. Option D becomes the correct answer. SGD1 class SVM is a versatile outlier detection model that excels in various scenarios, particularly those involving high-dimensional sparse datasets in both linear and nonlinear outlier detection. SGD1 class SVM D. All of the above. In financial transactions, identifying fraudulent activities like credit card fraud, money laundering, and account takeover attempts, the model can flag unusual transaction patterns or account behaviors that deviate from normal user profiles. This can help prevent financial losses and protect customer accounts. Detecting malicious network traffic or intrusion attempts by analyzing network logs and identifying patterns that deviate from typical network activity. This helps prevent cyber attacks and ensure network security. Identifying defective products or manufacturing errors by analyzing sensor data from production lines. The model can flag any unusual readings or deviations from expected product specifications, enabling quality control and reducing production waste. Imagine you are analyzing a dataset of credit card transactions for potential fraud. Each transaction is represented by features like transaction amount, time, location, and merchant category. You suspect fraudulent transactions might involve significantly higher transaction amounts than normal: 10, 20, 15, 30, 25, 500, 1000, 750. You train an SGD1 class SVM model on the normal transactions. The model learns a boundary around the normal transaction data. Any transactions outside this boundary are considered potential outliers or fraudulent transactions. In this scenario, the fraudulent transactions 500, 1000, 750 would fall far outside the boundary learned by the model, thus being flagged as potential outliers or fraudulent transactions. What is the best way to predict the value of a house using linear regression in sklearn? Sklearn. Train a linear regression model on the entire dataset and use it to predict the price of a new house. Split the dataset into training and testing sets. Train a linear regression model on the training set and use it to predict the price of a new house. Use a different machine learning model, such as a random forest regressor, to predict the price of a new house. All of the above. Train a linear regression model on the entire dataset and use it to predict the price of a new house. This approach would lead to overfitting, where the model learns the training data too well and fails to generalize to new, unseen data. Training on the entire dataset and then predicting on new data will not tell us how well the model generalizes to unseen data. Split the dataset into training and testing sets. Train a linear regression model on the training set and use it to predict the price of a new house. This is the best approach because it allows for model evaluation and helps to prevent overfitting. The model is trained on the training data and its performance is assessed on the testing data. This gives a better understanding of how well the model will generalize to new data. Splitting the dataset is crucial for evaluating the model's performance. Training on the training set allows the model to learn the relationships between the features in the target variable house price. Using the trained model to predict the price of a new house lets us evaluate how well the model generalizes to new, unseen data. Use a different machine learning model, such as a random forest regressor, to predict the price of a new house. While other models can be used, the question specifically asks for the best way to predict house prices using linear regression. Therefore, this option is not the best fit. The linear regression class in sklearn provides a straightforward way to implement linear regression in Python. All of the above. This option is incorrect because not all of the choices are valid approaches to using linear regression effectively. This option is incorrect because not all of the choices are valid approaches to using linear regression effectively. Split the dataset into training and testing sets. Train a linear regression model on the training set and use it to predict the price of a new house. A statistical method used to model the relationship between a dependent variable, e.g., house price, and one or more independent variables, e.g., square footage, number of bedrooms. Predicting house prices based on factors like size, location, and amenities. Estimating the cost of a project based on its duration and resources. Consider predicting the price of a house-dependent variable based on its square footage independent variable. Using historical data, you can build a linear regression model that predicts the price based on the square footage. This model might be represented as price AB square footage, where A and B are the coefficients determined by the linear regression analysis. Dividing a dataset into two or more subsets, typically training and testing sets. This allows for training a model on a portion of the data and evaluating its performance on unseen data. Training a machine learning model to recognize handwritten digits by splitting the dataset into training and test sets. The model is trained on the training set and its performance is evaluated on the test set to assess its ability to generalize to unseen digits. Splitting a customer dataset into training and test sets to train a model that predicts customer churn. The model is trained on the training set and its performance is evaluated on the test set to gauge its accuracy in identifying customers who are likely to churn. Imagine you have a dataset with 100 data points. You can split it into a training set of 80 data points and a testing set of 20 data points. This ensures that the model is trained on a significant portion of the data and its performance is assessed on a separate, unseen portion. The process of feeding the training data to a machine learning model to enable it to learn underlying patterns and relationships between features and the target variable. Training a spam filter on a dataset of emails labeled as spam or not spam. The filter learns patterns from the training data and then can predict whether a new email is spam. Training a recommendation system on a dataset of user preferences. The system learns patterns from user data and then can suggest relevant products or services to users. In a linear regression model, training involves finding the best fit line that minimizes the difference between predicted values and actual values. This is often done using algorithms like gradient descent. Assessing the performance of a trained model using metrics that measure its accuracy, precision, recall, or other relevant criteria. Evaluating a chatbot's performance by measuring its ability to understand user queries and provide relevant responses. Metrics like accuracy and user satisfaction are used to assess its effectiveness. Evaluating a fraud detection system by measuring its ability to identify fraudulent transactions. Metrics like precision and recall are used to evaluate its accuracy in flagging fraudulent activity. Common evaluation metrics for linear regression include mean squared error (MSE) and R-squared. MSE measures the average squared difference between predicted and actual values, while R-squared represents the proportion of variation in the dependent variable explained by the model. A metric used to measure the average squared difference between predicted values and actual values. In a regression model, evaluating the accuracy of a model predicting sales revenue. A lower MSE indicates better predictive performance. Assessing the performance of a model predicting customer churn. A lower MSE implies the model is better at predicting which customers are likely to churn. Let's say a model predicts the price of a house to be $300,000. But the actual price is $320,000. The squared error would be 300,320, 0.002 400 million. MSE is calculated by averaging the squared errors across all predictions. A popular Python library for machine learning that provides a wide range of algorithms, tools, and utilities for data analysis, modeling, and evaluation. Building a spam filter using scikit-learn's classification algorithms. The library provides models like naive Bayes and support vector machines that can effectively classify emails as spam or not spam. Creating a movie recommendation system using scikit-learn's clustering algorithms. The library's clustering algorithms can group users with similar preferences, enabling targeted recommendations. In scikit-learn, you can use the linear regression class to implement linear regression. The fit method trains the model on the training data, and the predict method makes predictions on new data. The mean squared error function can be used to calculate the MSE of the model. A powerful Python library for data manipulation and analysis, offering tools for reading, cleaning, transforming, and analyzing data in a tabular format. Loading a CSV file containing customer data into a pandas data frame. You can then use pandas functions to manipulate the data, such as filtering, sorting, and grouping customers based on specific criteria. Analyzing sales data by grouping sales by product category and calculating the total sales for each category. Pandas provides flexible data manipulation capabilities for data analysis. You can use pandas to read a CSV file into a data frame data PD, read CSV sales data.csv. Then, you can perform calculations like calculating the average sales data sales, mean. Pandas makes it easy to work with tabular data in Python, a fundamental Python library for numerical computation, providing powerful data structures like arrays and matrices, along with mathematical functions for manipulating them. Performing matrix operations in machine learning, such as calculating dot products and matrix multiplications, which are essential for many algorithms. Generating random numbers for tasks like initializing the weights of a neural network or splitting data into training and testing sets. You can use NumPy to create arrays array NP, array 1, 2, 3. You can then perform mathematical operations on these arrays, like adding two arrays array. Question: which of the following best describes the primary purpose of ridge regression in machine learning? A. To minimize the impact of outliers in the data. B. To prevent overfitting by adding a penalty term to the loss function. C. To improve model interpretability by selecting the most important features. D. To increase the computational efficiency of the model training process. Incorrect. While ridge regression can make models more robust to some degree, its primary focus is not on handling outliers directly. Techniques like robust regression are specifically designed to deal with outliers. A. To minimize the impact of outliers in the data. Correct. Ridge regression is known for its ability to prevent overfitting by adding a penalty term to the loss function. This penalty term, known as L2 regularization, directly discourages large coefficient values in the model. By shrinking the coefficients, it helps prevent the model from becoming too sensitive to individual data points, leading to better generalization performance. B. To prevent overfitting by adding a penalty term to the loss function. Incorrect. While ridge regression can sometimes lead to smaller coefficients, it doesn't explicitly select features. This is a characteristic of L1 regularization lasso. C. To improve model interpretability by selecting the most important features. Incorrect. Ridge regression does not directly improve computational efficiency. It focuses on improving the model's generalization performance. D. To increase the computational efficiency of the model training process. B. Ridge regression is a type of linear regression that adds a penalty term to the loss function to shrink the coefficients towards zero. This penalty term is the sum of the squared coefficients. By shrinking the coefficients, ridge regression prevents overfitting and improves the model's generalization performance on unseen data. Question: which of the following best describes the primary purpose of ridge regression in machine learning? Overfitting occurs when a machine learning model learns the training data too well, resulting in poor performance on unseen data. This happens because the model memorizes the training data's idiosyncrasies and fails to generalize to new examples. Solution: L2 regularization is a technique used in ridge regression where the penalty term is proportional to the sum of the squared coefficients. This penalty term discourages large coefficients, leading to a more stable and less overfitted model. Solution: Generalization performance refers to the ability of a machine learning model to perform well on unseen data. A model with good generalization performance can accurately predict outcomes for new inputs that were not part of the training data. Solution: A loss function is a mathematical function that measures the error of a machine learning model. The goal of training a model is to minimize the loss function, which means reducing the model's error. Solution: In linear regression, coefficients represent the weights associated with each feature. They determine the strength and direction of the relationship between a feature and the target variable. For example, a positive coefficient indicates a positive correlation, while a negative coefficient indicates a negative correlation. Solution: Ridge regression is used in various domains, including predicting housing prices, analyzing stock market trends, and modeling customer behavior. In each case, the model aims to learn complex relationships between multiple input features and the target variable, often with the risk of overfitting. Use cases: The sklearn library in Python provides a straightforward implementation of ridge regression. The code snippet demonstrates how to create, train, and predict using a ridge regression model, allowing you to experiment with the alpha parameter and observe its effect on model behavior. This allows you to control the strength of L2 regularization and adjust the model's sensitivity to features. Sklearn implementation. Which of the following statements accurately describes the purpose of a sklearn linear model ridge CV class? A. Performs cross-validation to determine the optimal regularization parameter alpha for ridge regression. B. Fits a ridge regression model using a predefined alpha value. C. Applies lasso regularization to minimize the model's complexity. D. All of the above. A. Performs cross-validation to determine the optimal regularization parameter alpha for ridge regression. True. This statement is correct. Ridge CV uses cross-validation to search for the best regularization parameter alpha that minimizes the model's error on unseen data. This process involves dividing the dataset into multiple folds and training and evaluating a model on different combinations of folds. By comparing the performance across different alpha values, Ridge CV selects the one that achieves the best generalization on the unseen data. B. Fits a ridge regression model using a predefined alpha value. False. This statement is incorrect. Ridge CV doesn't utilize a predefined alpha value. Instead, it actively searches for the optimal alpha using cross-validation. This search allows Ridge CV to determine the best value of alpha that balances bias and variance, minimizing the model's error on unseen data. C. applies lasso regularization to minimize the model's complexity. False. This statement is incorrect. Ridge CV employs L2 regularization, also known as ridge regularization. Lasso regularization, on the other hand, uses L1 regularization. These regularization methods differ in how they penalize the model's coefficients, leading to different effects on model complexity. D. All of the above. False. This statement is incorrect because options B and C are false. While ridge CV does utilize ridge regression, it doesn't fit a model with a predefined alpha value, nor does it apply lasso regularization. A. Performs cross-validation to determine the optimal regularization parameter alpha for ridge regression. Ridge regression, a linear regression technique that uses L2 regularization to prevent overfitting. It adds a penalty term to the loss function proportional to the square of the magnitude of A. Coefficients. Predicting housing prices. When predicting housing prices based on features like size, location, and number of bedrooms, ridge regression can help prevent overfitting and produce a model that generalizes well to unseen houses. It can handle cases where some features might have a high correlation with the target variable, thus preventing the model from being overly sensitive to those features. Regularization, a technique used to prevent overfitting by adding a penalty term to the loss function, which discourages complex models. Financial forecasting. When forecasting stock market trends, regularization can help avoid models that are overly tailored to past data and perform poorly on future trends. By preventing overfitting, regularization helps create more robust models that are less prone to fluctuations in market data. L2 regularization, a specific type of regularization that penalizes the sum of squared coefficients. This encourages smaller coefficient values, making the model less sensitive to individual features. Predicting customer churn. When analyzing customer data to predict churn, L2 regularization can prevent overfitting and ensure that the model isn't overly influenced by specific customer features that might be atypical. By shrinking the coefficients, L2 regularization makes the model more robust and less likely to be swayed by outliers in the data. Cross-validation, a technique used to evaluate the performance of a machine learning model on unseen data. It involves splitting the dataset into multiple folds and training and testing the model on different combinations of folds. Recommending products. Cross-validation can be employed to evaluate the performance of a recommendation system. By splitting the data into folds and training and testing the model on different folds, you can assess the recommendation system's ability to suggest relevant products to new users based on their preferences. Alpha parameter, a hyperparameter in ridge regression that controls the strength of L2 regularization. A higher alpha value imposes a stronger penalty, leading to simpler models with smaller coefficients. Optimizing investment strategies. When developing an investment strategy, the alpha parameter can be used to adjust the model's complexity. A higher alpha value might result in a simpler strategy that relies less on individual factors and is more conservative, while a lower alpha value might lead to a more complex strategy that captures more nuanced market signals. 1, 2, 3, 4, 5, 2, 4, 6, 8, 10. In this example, we have a simple dataset with 5 data points. The goal is to fit a linear regression model that predicts the value of y based on x. Without regularization, the model might overfit the data, resulting in a line that perfectly passes through all the data points. However, this model might not generalize well to new data. Ridge regression with ridge CV can help overcome this issue. By searching for the optimal alpha value through cross-validation, Ridge CV ensures that the model finds a balance between fitting the data and generalizing well to unseen data. This balance is crucial for creating a reliable and robust model that performs well in real-world scenarios. Which of the following parameters in sklearn SGD regressor can be used to control the learning rate? A. Learning rate. B. Eta 0. C. Alpha. D. All of the above. Explanation: the learning rate parameter in SGD regressor defines the initial learning rate and controls how it changes over time based on the chosen learning rate schedule, e.g. constant, optimal, in-view scaling, adaptive, related concept learning rate schedules. Use cases: adjusting the learning rate during training to improve convergence or handle plateauing. In the loss function, explanation: eta 0 represents the initial learning rate in SGD regressor. The learning rate can be adjusted based on the chosen schedule using learning rate related concept learning rate schedules. Use cases: setting the initial learning rate for the optimization process. Explanation: alpha in SGD regressor controls the strength of L2 regularization. Regularization adds a penalty term to the loss function, pushing model weights towards 0, while indirectly influencing learning by reducing the magnitude of weights. It's primarily used to prevent overfitting. Related concept regularization. Use cases: controlling overfitting by limiting the complexity of the model and improving its generalization ability to unseen data. Explanation: learning rate, eta 0, and alpha all affect the learning process, each in its own way, contributing to controlling the rate at which the model learns. The learning rate directly affects the size of steps taken during gradient descent, while alpha influences learning indirectly by penalizing complex models. Related concepts: learning rate, stochastic gradient descent, regularization. Use cases: large-scale datasets, online learning where data arrives sequentially, situations where computational efficiency is crucial. D. All of the above. Which of the following statements accurately describe the elastic net regularization technique in machine learning? A. It combines the strengths of L1 and L2 regularization, providing a balance between feature selection and model stability. B. It can handle high-dimensional datasets with many features, effectively reducing overfitting. C. It allows for a tunable parameter alpha to control the degree of regularization. D. All of the above. It combines the strengths of L1 and L2 regularization, providing a balance between feature selection and model stability. This statement is correct. Elastic net is a linear regression model that combines L1 lasso and L2 ridge regularization. L1 encourages sparsity by setting some coefficients to 0, effectively performing feature selection. L2 promotes stability by shrinking coefficients towards 0, but doesn't necessarily set them to 0. By combining both, elastic net offers the advantages of both L1 and L2 regularization. It performs feature selection while maintaining model stability. True. Elastic net regularization, L1 regularization lasso, L2 regularization ridge, feature selection, model stability. It can handle high-dimensional datasets with many features, effectively reducing overfitting. This statement is correct. Elastic net's ability to perform feature selection and maintain model stability makes it particularly effective for handling high-dimensional datasets. By reducing the number of relevant features, it helps prevent overfitting, which occurs when a model learns the training data too well and performs poorly on unseen data. True. Elastic net regularization, overfitting, high-dimensional datasets. It allows for a tunable parameter alpha to control the degree of regularization. This statement is correct. ElasticNet introduces a parameter called alpha to control the balance between L1 and L2. Regularization. A higher alpha value places more emphasis on L1 regularization, leading to greater sparsity feature selection. A lower alpha value emphasizes L2 regularization, promoting model stability. By adjusting alpha, you can fine-tune the regularization strength based on your dataset and modeling goals. True. ElasticNet regularization, alpha parameter. All of the above. This statement is correct because all the above statements A, B, and C accurately describe the ElasticNet regularization technique. True. ElasticNet regularization. L1 regularization lasso. L2 regularization ridge. Feature selection. Model stability. Overfitting. High-dimensional datasets. Alpha parameter. D. All of the above. Regularization. L1 regularization lasso. L2 regularization ridge. Overfitting. Feature selection. Model stability. High-dimensional datasets. Genetic analysis identifying important genes from high-dimensional gene expression data. Image recognition classifying images with a large number of features. Text analysis building predictive models for sentiment analysis or topic modeling. Financial modeling predicting stock prices or credit risk based on various economic indicators. In this scenario, we have a dataset with 10 features, represented by the matrix X, and a target variable Y. We want to fit a linear model to predict Y using X. However, we know that some features might be irrelevant or redundant, causing overfitting. We use ElasticNet to address this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 10, 20, 30. From sklearn, linearmodel import ElasticNet. Model ElasticNet alpha 0.5. L1 ratio 0.7. Model, physics, Y. Print model, core, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0.1. Which statement best describes the ElasticNet CV model in scikit-learn? A. A linear regression model that combines L1 and L2 regularization using a fixed ratio. B. A linear regression model that automatically searches for the optimal alpha and L1 ratio for regularization. C. A linear regression model with built-in cross-validation for feature selection. D. All of the above. A. A linear regression model that combines L1 and L2 regularization using a fixed ratio. False. While ElasticNet CV combines L1 and L2, it doesn't use a fixed ratio. It dynamically searches for the optimal ratio L1 ratio through cross-validation. This statement is partially true but doesn't capture the dynamic aspect of ElasticNet CV. B. A linear regression model that automatically searches for the optimal alpha and L1 ratio for regularization. True. This is the core functionality of ElasticNet CV. It utilizes cross-validation CV to automatically determine the best values for alpha overall, regularization strength and L1 ratio L1-L2 balance from a predefined range. This process ensures the model's generalization capability and optimal performance. C. A linear regression model with built-in cross-validation for feature selection. True. This statement is correct. The CV in ElasticNet CV signifies that it inherently performs cross-validation. This cross-validation is instrumental in selecting the best features. L1 regularization lasso within ElasticNet promotes sparsity, pushing some coefficients towards zero, effectively selecting the most relevant features. D. All of the above. True. This is the correct answer. All the previous statements accurately describe the ElasticNet CV model. It combines L1 and L2 regularization, automatically searches for the optimal parameters, and performs cross-validation for feature selection. D. All of the above. A technique used to prevent overfitting in machine learning models. It introduces constraints on the model's coefficients, reducing their magnitude and preventing them from taking extreme values. Imagine you are trying to predict the price of a house based on its size, location, and age. Overfitting could occur if the model gives too much weight to a specific feature, like size, making it overly sensitive to that factor. Regularization helps to balance the influence of various features, preventing the model from relying heavily on a single factor. Consider a linear regression model with the equation yb0 b1 x1 b2 x2. Without regularization, the coefficients b1 and b2 could become very large, leading to a model that's too sensitive to small changes in the input features. Regularization adds a penalty term to the cost function, discouraging large coefficients and promoting more balanced influence of features. Adds a penalty term proportional to the absolute values of the coefficients. This encourages sparsity, pushing some coefficients towards zero, leading to feature selection. Think of a medical diagnosis model predicting the likelihood of a disease based on various symptoms. L1 regularization can help identify the most crucial symptoms for the diagnosis by shrinking coefficients of less relevant symptoms to zero. This results in a more interpretable model, focusing on the most significant indicators. In a linear regression model, the L1 penalty is calculated as L1 alpha sumubs coefficients. The higher the alpha value, the stronger the penalty, forcing some coefficients to become zero, leading to feature selection. Adds a penalty term proportional to the squared values of the coefficients. This shrinks coefficients towards zero but avoids pushing them completely to zero. It helps to improve model stability and reduce overfitting. Imagine a financial model predicting stock prices based on various economic indicators. Ridge regularization can help stabilize the model by preventing any single indicator from having an overly dominant influence. This reduces the risk of the model becoming overly sensitive to small changes in specific indicators. The L2 penalty is calculated as L2 alpha sum coefficients 2. This penalty tends to shrink coefficients towards zero but doesn't eliminate them entirely, contributing to model stability. A technique used to evaluate the performance of a machine learning model on unseen data. It involves splitting the data into multiple folds, training the model on a subset, and evaluating it on the remaining fold. This process is repeated for different folds to estimate the model's generalization ability. Imagine developing a spam detection system. You can use cross-validation to evaluate the model's ability to identify spam emails in a real-world setting. By splitting the email dataset into folds and training on different subsets, you can assess how well the model generalizes to unseen emails, ensuring its effectiveness in filtering spam. Consider a dataset of 100 samples. You can split it into 5 folds of 20 samples each. Train the model on 4 folds 80 samples and evaluate its performance on the remaining fold 20 samples. Repeat this process with different combinations of training and evaluation folds to get a robust estimate of the model's performance. A hyperparameter in regularization techniques that controls the overall strength of regularization. A higher alpha value implies stronger regularization, leading to smaller coefficients and potentially more feature selection. Imagine a machine learning model predicting customer churn based on various factors like demographics, purchase history, and engagement metrics. You can adjust the alpha parameter to control how strongly the model penalizes complex relationships. A higher alpha can help simplify the model, focusing on the most influential factors for predicting churn. In both L1 and L2 regularization, the alpha parameter multiplies the penalty term. A higher alpha value increases the penalty, pushing coefficients towards 0 and potentially leading to feature selection. A hyperparameter in elastic net that controls the balance between L1 and L2 regularization. It ranges from 0 to 1, where 0 corresponds to pure L2 ridge and 1 corresponds to pure L1 lasso. Values in between represent a combination of both regularization techniques. Imagine a model predicting loan defaults based on various borrower characteristics. You can adjust the L1 ratio to balance between feature selection L1 and model stability L2. A higher L1 ratio would favor L1 regularization, leading to a simpler model with fewer features, while a lower value would focus more on stability. In elastic net, the penalty term combines L1 and L2 penalties. Elastic net alpha L1 ratio L11 L1 ratio L2. By adjusting the L1 ratio, you can control the relative influence of L1 and L2 regularization on the model's coefficients. The process of selecting the most relevant features from a dataset for a machine learning model. This can improve model performance by reducing noise and complexity. Elastic Net CV facilitates feature selection through its L1 regularization component. Imagine a marketing campaign model predicting customer response to targeted ads based on various demographic and behavioral data. Feature selection can help identify the most impactful attributes for targeting, improving campaign effectiveness and resource allocation. Consider a dataset with 10 features. Using Elastic Net CV, the model can identify the 3 most relevant features for predicting the target variable. This reduces the dimensionality of the problem, simplifying the model and potentially improving its accuracy. A situation in which a machine learning model learns the training data too well, leading to poor generalization performance on unseen data. Regularization techniques, like Elastic Net, help mitigate overfitting by controlling the complexity of the model. Imagine a spam detection model trained on a specific set of spam emails. Overfitting could occur if the model becomes overly sensitive to the specific patterns in those emails, leading to poor performance on new spam emails with different patterns. Imagine a model with a high degree of complexity, e.g., a polynomial regression with a high order. This model could fit the training data perfectly but might not generalize well to new data. Exhibiting overfitting. Regularization helps to reduce the complexity of the model by shrinking coefficients and preventing excessive fitting to the training data. 1. High-dimensional data analysis. Elastic Net CV is well suited for handling datasets with many features, especially when some features might be correlated or irrelevant. Genomics data analysis often involves datasets with thousands of genes. Elastic Net CV can effectively identify the most relevant genes for predicting a specific disease outcome, even in the presence of high correlation between genes. 2. Feature selection. It automatically identifies and selects the most important features. improving model interpretability and reducing complexity. In image recognition, Elastic Net CV can help identify the key features like edges, textures, or shapes that are most discriminative for classifying different objects, leading to more insightful and efficient models. 3. Regularized regression. Elastic Net CV provides a balanced approach to regularization, combining the benefits of L1 feature selection and L2 stability in preventing overfitting. In financial forecasting, Elastic Net CV can be used to predict market trends based on various economic and social indicators. Its combination of L1 and L2 regularization helps to identify key drivers of market movements while preventing overfitting to noisy data. Which of the following statements accurately describes the least angle regression LAS algorithm in scikit-learn? A. LAS is a greedy algorithm that sequentially adds predictors to a model based on their correlation with the target variable. B. LAS computes the entire solution path for all possible values of the regularization parameter. C. LAS is particularly efficient for high-dimensional datasets with many features. D. All of the above. A. LAS is a greedy algorithm that sequentially adds predictors to a model based on their correlation with the target variable. This statement is correct. LAS is a greedy algorithm because it iteratively adds predictors to the model based on their correlation with the target variable. It starts with the predictor that has the highest correlation and then proceeds to add other predictors in a stepwise manner, always choosing the predictor that has the highest correlation with the current residual. True. B. LAS computes the entire solution path for all possible values of the regularization parameter. This statement is also correct. LAS is designed to compute the entire solution path for all possible values of the regularization parameter. This means that you get a complete set of models with different levels of regularization, allowing you to choose the best model based on your needs. True. C. LAS is particularly efficient for high-dimensional datasets with many features. This statement is also correct. LAS is particularly efficient for high-dimensional datasets because it only needs to compute a small number of models, unlike other regression methods that might need to explore all possible feature combinations. This efficiency stems from its greedy approach of sequentially adding predictors based on correlation. True. D. All of the above. Since all the statements are correct, this option is also correct. True. D. All of the above. LT font style quote font size 12px quotient least angle regression LAS LT font EGT. LAS is a regression algorithm that constructs a solution path by iteratively adding variables to the model, starting with the variable that has the highest correlation with the response variable. Feature selection, regularization, sparse models, robustness, LT font style quote font size 12px quotient regularization LT font GT. Regularization is a technique used to prevent overfitting in machine learning models. By adding a penalty to the loss function, it encourages simpler models with fewer parameters, preventing overfitting in machine learning models. Encouraging simpler models with fewer parameters. LT font style quote font size 12px quotient solution path LT font GT. The solution path represents all possible model solutions for different values of a regularization parameter. It allows you to choose the optimal model based on your desired level of regularization. Choosing the optimal model based on the desired level of regularization. Understanding the impact of different regularization strengths on the model. LT font style quote font size 12px quotient greedy algorithm LT font GT. A greedy algorithm makes locally optimal decisions at each step, hoping to find a globally optimal solution. In LAS, it greedily selects the variable with the highest correlation and adds it to the model, finding approximate solutions to complex optimization problems. Efficiently solving problems where finding the exact solution is computationally expensive. LT font style font size 12px GT high dimensional dataset SLT font EGT. High dimensional datasets have a large number of features compared to the number of samples. LAS is particularly efficient for such datasets because it doesn't require computing all possible feature combinations, as other methods might. Analyzing datasets with a large number of features. Building models with a large number of predictor variables. LT font style font size 12px GT sparse model SLT font EGT. Sparse models have a small number of non-zero coefficients, which can make them easier to interpret and understand. LAS can create sparse models by shrinking the coefficients of less important features to zero. Improving model interpretability, reducing the complexity of models. Identifying important features in high-dimensional datasets. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 2, 5, 8, 11. Let's consider a simple example with 4 data points and 3 features. The LAS algorithm would start by finding the feature with the highest correlation with the target variable. In this case, let's assume the first feature has the highest correlation. Then, LAS would move along the direction of the first feature until it hits another feature that has the same correlation with the target variable. Let's say the second feature has the same correlation. At this point, LAS would move along a direction that is equally correlated with both the first and second features, continuing this process until it reaches a solution. What is the purpose of using LAS-CV in scikit-learn's linear model? To perform a ridge regression by adding L2 regularization to the loss function. To select the optimal number of features in a linear model by performing L1 regularization and feature elimination based on a regularization path. To perform a lasso regression by applying L1 regularization, thereby selecting the optimal number of features and shrinking irrelevant coefficients to zero. All of the above, true. LAS-CV incorporates L2 regularization, which adds a penalty to the sum of squared coefficients, thereby preventing overfitting and resulting in ridge regression. This is mentioned in the solution explanation block under to combat overfitting. L2 regularization is also incorporated, adding a penalty to the sum of squared coefficients, resulting in ridge regression. True. LAS-CV utilizes L1 regularization, which shrinks irrelevant features to zero, leading to feature selection. This is mentioned in the solution explanation block under this process involves applying L1 regularization, which shrinks irrelevant features to zero, leading to feature selection. True. LAS-CV employs L1 regularization to select the optimal number of features and shrink irrelevant coefficients to zero, achieving the effect of lasso regression. This is mentioned in the solution explanation block under finally. LAS-CV leverages cross-validation to determine the optimal regularization parameter, yielding both lasso regression and ridge regression effects. True. The correct answer is D, as LAS-CV combines the functionalities of ridge regression L2 regularization, lasso regression L1 regularization, and feature selection. This is mentioned in the solution explanation block under LAS-CV. A scikit-learn linear model accomplishes all these tasks within the realm of linear regression. D. All of the above. A statistical method that aims to establish a linear relationship between a dependent variable output and one or more independent variables inputs. Predicting housing prices based on factors like size, location, and number of bedrooms. Estimating sales revenue based on marketing expenditure and customer demographics. Forecasting product demand based on historical sales data and seasonal trends. A technique that iteratively adds features to a linear model. Controlling the complexity by moving along the direction of the most correlated features. Identifying key variables in a large-scale genetic study to understand the relationship between genes and disease. Analyzing customer purchase data to identify the main drivers of customer satisfaction. Optimizing advertising campaigns by identifying the most effective ad channels. A technique used to prevent overfitting in machine learning models by adding a penalty term to the loss function. Improving the accuracy of a spam detection model by preventing the model from memorizing the training data. Enhancing the stability of a financial risk prediction model by reducing the impact of noise in the data. Making a machine translation model more robust to variations in input language. A type of regularization that adds a penalty proportional to the absolute value of the model. Coefficients, leading to sparse solutions where irrelevant features are shrunk to zero. Selecting a subset of relevant genes from a large-scale gene expression dataset for disease. Diagnosis, simplifying a complex model by removing unnecessary features, leading to easier interpretation and improved performance. Identifying the key factors that influence customer churn in a telecommunications company. Lasso loss function loss sumubs coefficients 2, -1, 0, 5, 0.5, loss 0.5 ABS2 ABS1 ABS0 ABS5. A type of regularization that adds a penalty proportional to the squared value of the model. Coefficients, leading to shrinkage of coefficients towards zero. Improving the accuracy of a credit risk prediction model by reducing the impact of high variance. Features. Making a stock price prediction model more stable by controlling the influence of individual stocks on the overall prediction. Enhancing the robustness of a sentiment analysis model to variations in input text. Ridge loss function loss sum coefficients 2, -1, 0, 5, 0.5, loss 0, 5, 22, 12, 02, 52. A technique used to evaluate the performance of a machine learning model by splitting the data into multiple folds, training the model on different combinations of folds, and averaging the performance across all folds. Assessing the generalizability of a fraud detection model to new data. Selecting the optimal hyperparameters for a recommender system based on user preferences. Comparing different machine learning algorithms for a given task to identify the best performing. 1. The process of selecting a subset of relevant features from a dataset for use in a machine learning model. Reducing the dimensionality of a high-dimensional dataset for efficient analysis and visualization. Improving the performance of a classification model by removing noisy or redundant features. Making a regression model more interpretable by identifying the key factors that influence the target variable. A phenomenon where a machine learning model learns the training data too well, resulting in poor performance on unseen data. A spam detection model that incorrectly classifies legitimate emails as spam because it has learned to identify patterns specific to the training data. A stock price prediction model that fails to predict future prices accurately because it has memorized past price trends instead of learning the underlying market dynamics. A machine translation model that produces unnatural or grammatically incorrect translations because it has overfitted to the training data. A property of a model where a large proportion of coefficients are equal to 0, leading to simpler and more interpretable models. A gene expression model that identifies only a small number of genes as being significantly associated with a disease. A customer segmentation model that identifies only a few key customer attributes as being responsible for different spending patterns. A recommender system that only suggests products that are highly relevant to a user's interests. The ability to understand how a machine learning model works and why it makes certain predictions. Explaining the reasons behind a loan approval decision to a borrower. Identifying the factors that influence a customer's likelihood to purchase a product. Understanding the reasoning behind a medical diagnosis based on patient data. The ability of a machine learning model to maintain its performance even when faced with noisy or corrupted data. A fraud detection model that can accurately identify fraudulent transactions even when the data contains errors or outliers. A weather forecasting model that can make accurate predictions even when faced with incomplete or inaccurate weather data. A machine translation model that can produce accurate translations even when the input text contains typos or grammatical errors. Datasets with a large number of features compared to the number of data points. Gene expression data, where each feature represents the expression level of a gene and the number of features can be in the thousands. Image data, where each pixel can be considered a feature and the total number of pixels can be millions. Text data, where each word can be considered a feature and the number of unique words in a corpus can be very large. Which of the following statements is true about lasso regression in scikit-learn? Sklearn, linear model, lasso. A. Lasso regression is a type of linear regression that performs feature selection by shrinking k coefficients of less important features towards 0. B. Lasso regression can be used for both classification and regression tasks. C. Lasso regression is highly robust to outliers. D. All of the above. A. Lasso regression is a type of linear regression that performs feature selection by shrinking k coefficients of less important features towards 0. Correct. Lasso regression is a type of linear regression that utilizes L1 regularization. L1 regularization adds a penalty term to the loss function proportional to the absolute values of the coefficients. This penalty encourages the model to shrink the coefficients of less important features towards 0, effectively performing feature selection. By setting some coefficients to 0, lasso regression automatically eliminates the corresponding features, simplifying the model and improving interpretability. A. Lasso regression is a type of linear regression that performs feature selection by shrinking k coefficients of less important features towards 0. B. Lasso regression can be used for both classification and regression tasks. Correct. While primarily used for regression tasks, lasso regression can be adapted for classification problems by employing a suitable loss function, such as logistic loss. This allows lasso to predict class probabilities, making it suitable for binary or multi-class classification scenarios. B. Lasso regression can be used for both classification and regression tasks. C. Lasso regression is highly robust to outliers. Partially correct. Lasso regression does exhibit some level of robustness against outliers due to the regularization effect, which prevents coefficients from becoming excessively large. However, it's not as robust as methods specifically designed for outlier handling, like robust regression, for datasets with significant outliers. Employing outlier detection and handling techniques before applying lasso regression is often recommended. C. Lasso regression is highly robust to outliers. D. All of the above. Correct. All the statements about lasso regression are true, making D. All of the above the correct answer. Lasso regression combines the benefits of linear regression with the ability to perform feature selection and, to some extent, handle outliers. D. All of the above. D. Linear regression. Predicting a continuous target variable based on a linear combination of input features. For example, predicting a house price based on its size, location, and number of bedrooms, predicting housing prices, forecasting sales trends, estimating customer lifetime value, regularization, adding a penalty term to the loss function to prevent overfitting and improve model generalization. This helps the model avoid becoming too complex and perform better on unseen data. Preventing overfitting in image classification models. Improving the accuracy of financial risk prediction models. Enhancing the stability of recommendation systems. L1 regularization. A type of regularization that adds a penalty proportional to the absolute value of the coefficients. This forces less important features to have zero coefficients. Effectively performing feature selection. Identifying key factors influencing customer churn. Selecting relevant genes for disease prediction. Optimizing advertising campaigns by identifying effective ad placements. Feature selection. The process of identifying the most relevant features for a model. Reducing dimensionality and improving performance. It helps simplify models, reduce noise, and improve interpretability. Simplifying fraud detection models by focusing on crucial indicators. Improving the speed and accuracy of text classification models. Reducing the complexity of medical diagnosis models. Overfitting. When a model learns the training data too well, leading to poor performance on unseen data. This can occur when the model becomes too complex and memorizes the training data instead of generalizing to new examples. A spam filter that incorrectly flags legitimate emails as spam. A medical diagnosis model that misclassifies healthy patients as having a disease. A stock prediction model that fails to accurately predict future market movements. Robustness. The ability of a model to perform well even when the data contains outliers or noise. Robust models are less susceptible to the influence of extreme values. Predicting customer satisfaction even when survey data contains biased responses. Analyzing financial data that may include errors or outliers. Detecting anomalies in sensor readings despite potential noise. Ridge regression. Another type of linear regression that uses L2 regularization. Shrinking coefficients towards zero but not necessarily to zero. It is less effective for feature selection than lasso but offers better robustness against outliers. Improving the accuracy of weather forecasting models. Stabilizing financial risk models by reducing the impact of volatility. Enhancing the reliability of predictive maintenance models. Scikit-learn sklearn. A popular Python library for machine learning, providing various algorithms and tools for data analysis, model building, and evaluation. Building machine learning models for image recognition, natural language processing, and time series analysis. Developing AI-powered applications for healthcare, finance, and marketing. Conducting research and experimentation in machine learning. 1000, 1500, 2000, 2500, 3000, 1500, 2200, 2800, 3500, 400. Price intercept coefficient size. Loss function penalty term. Alpha sum coefficients L1 regularization. Imagine predicting house prices based on their size. Using lasso regression, the model learns the relationship between size and price. And by applying L1 regularization, it might identify that size is the most influential feature while other factors like location are less important. This means the coefficient for size will be relatively large, while the coefficients for less relevant features will be shrunk towards zero. In this way, lasso regression helps simplify the model and make it more interpretable. What is the primary purpose of the lasso CV class in the sklearn linearmodel module? A. To perform L1 regularization on a linear model and select the optimal regularization strength through cross-validation. B. To perform L2 regularization on a linear model and select the optimal regularization strength through cross-validation. C. To perform feature selection and coefficient shrinkage using L2 regularization. D. All of the above. A. To perform L1 regularization on a linear model and select the optimal regularization strength through cross-validation. True. This choice is correct. Lasso CV utilizes L1 regularization, which minimizes the sum of the absolute values of the model's coefficients. It employs cross-validation to find the optimal regularization strength alpha that minimizes the model's error on unseen data. B. To perform L2 regularization on a linear model and select the optimal regularization strength through cross-validation. False. This choice is incorrect. Lasso CV is specifically designed for L1 regularization, not L2. L2 regularization ridge adds a penalty term proportional to the squared sum of the coefficients. While both lasso CV and ridge CV use cross-validation for optimal parameter selection, they differ in their regularization methods. C. To perform feature selection and coefficient shrinkage using L2 regularization. False. This choice is incorrect. Lasso CV utilizes L1 regularization, not L2. L1 regularization encourages sparsity in the model, driving some coefficients to zero, resulting in feature selection. L2 regularization, on the other hand, shrinks coefficients towards zero without necessarily making them exactly zero. D. All of the above. True. This choice is correct. Lasso CV performs all the actions mentioned in the other choices: L1 regularization, feature selection, coefficient shrinkage, and optimal regularization strength selection through cross-validation. D. All of the above. L1 regularization adds a penalty term to the loss function proportional to the absolute value of the model's coefficients. This penalty encourages sparsity, driving some coefficients towards zero, effectively performing feature selection. Predicting customer churn in telecommunications using a model with a large number of features. Lasso can identify the most influential factors and create a more interpretable model. Cross-validation involves splitting the training data into multiple folds. The model is trained on a subset of the folds and evaluated on the remaining folds. This process is repeated multiple times, using different folds for training and evaluation. This helps estimate the model's performance on unseen data and prevents overfitting. Evaluating a machine learning model for medical image classification. Cross-validation ensures the model's accuracy is not overly dependent on a specific data split. Which of the following statements accurately describe the Lasso-Lars algorithm in scikit-learn? Lasso-Lars uses a greedy coordinate descent algorithm to find the optimal solution. It efficiently solves the lasso problem by iteratively adding and removing features. Lasso-Lars is particularly well suited for high-dimensional datasets. All of the above. LaSoulas uses a greedy coordinate descent algorithm to find the optimal solution. A. LaSoulas utilizes a LT font color co 0000FF quotient greedy coordinate descent algorithm LT font TGT to find the optimal solution. This means it iteratively selects the feature with the largest correlation with the target variable and updates the coefficients accordingly. True. It efficiently solves the lasso problem by iteratively adding and removing features. B. LaSoulas achieves efficient feature selection by LT font color co 0000FF quotient iteratively adding and removing features LT font TGT. This process is guided by the LaS algorithm, which calculates the path of coefficients as the penalty parameter changes. True. LaSoulas is particularly well suited for high-dimensional datasets. C. LaSoulas is particularly LT font color co 0000FF quotient well suited for high-dimensional dataset SLT font TGT. The algorithm 39's efficient feature selection mechanism excels in scenarios with numerous features, preventing overfitting and improving model generalization. True. All of the above. All the above statements are accurate descriptions of LaSoulas. It uses greedy coordinate descent, iteratively adds removes features, and is well suited for high-dimensional datasets. True. All of the above. LaSoulas is a powerful algorithm designed for feature selection and regularization. It implements the least angle regression LaS algorithm to solve the lasso problem. A greedy algorithm that iteratively selects the feature with the largest correlation with a target variable and updates the coefficients accordingly. In this process, each step aims to find the best possible local solution without considering the overall global optimality. Lasso least absolute shrinkage and selection operator is a linear regression method that uses L1 regularization to shrink the coefficients of less important features towards zero, effectively performing feature selection. Regularization is a technique used to prevent overfitting in machine learning models by adding a penalty term to the loss function. This penalty discourages complex models and encourages simpler solutions that generalize better to unseen data. The process of selecting the most relevant features from a dataset for a given prediction task. This helps to improve model performance by reducing noise and complexity. LaS is an algorithm that provides a solution path for linear regression models. It starts by identifying the feature most correlated with the target variable and then gradually adds other features to the model based on their correlation, while adjusting the coefficients of the selected features. Datasets with a large number of features compared to the number of observations. These datasets pose challenges for traditional machine learning algorithms due to the risk of overfitting and computational complexity. LaSoulas excels in handling such datasets. A situation where a machine learning model performs well on the training data but poorly on unseen data. This occurs when the model learns the training data too well, including its noise and peculiarities, and fails to generalize to new examples. The ability of a machine learning model to perform well on unseen data. A model that generalizes well can make accurate predictions on data it has never encountered before. In medical diagnosis, LaSoulas can be used to identify the most important biomarkers for predicting a specific disease from a large set of potential biomarkers. In fraud detection, LaSoulas can be used to build a model that effectively identifies fraudulent transactions from a large dataset of transactions, while preventing overfitting to specific patterns in the training data. In genetics research, LaSoulas can be used to analyze large datasets of gene expression data to identify genes associated with certain diseases or traits. Consider a dataset with 10 features and 100 observations. You want to build a linear regression model to predict the target variable. To illustrate how linearmodel performs feature selection, assume you have a penalty parameter that forces the model to select only 3 features. In this scenario, linearmodel, using its greedy coordinate descent algorithm, would iteratively choose the features most strongly correlated with the target variable, eventually selecting the 3 most relevant features for the given penalty parameter. Which of the following statements accurately describes the primary goal of the linearmodel CV algorithm in sklearn? A. To find the optimal regularization parameter alpha for a linearmodel model by minimizing the mean squared error MSE on a cross-validation set. B. To perform feature selection by shrinking the coefficients of less important features to 0, while simultaneously finding the best regularization parameter alpha. C. To identify the optimal number of features to include in a model by iteratively adding or removing features based on their importance. D. All of the above. True. Linearmodel CV uses cross-validation to determine the optimal alpha value, which controls the amount of regularization applied to the model. The key lies in its regularization parameter alpha. Linearmodel CV uses cross-validation to determine the optimal alpha value, which controls the amount of regularization applied to the model. True. By shrinking the coefficients of less important features towards 0, linearmodel CV effectively performs feature selection, leading to a more parsimonious model. By shrinking the coefficients of less important features towards 0, linearmodel CV effectively performs feature selection, leading to a more parsimonious model. True. Linearmodel CV effectively combines feature selection and regularization. It employs a technique called least angle regression LAS to iteratively build a model by adding features based on their correlation with the target variable. Linearmodel CV effectively combines feature selection and regularization. It employs a technique called least angle regression LAS to iteratively build a model by adding features based on their correlation with the target variable. At each step, it selects the feature with the highest correlation and updates the model. True. All the above statements accurately describe the primary goal of the linearmodel CV algorithm. Linearmodel CV effectively combines feature selection and regularization. It employs a technique called least angle regression LAS to iteratively build a model by adding features based on their correlation with the target variable. At each step, it selects the feature with the highest correlation and updates the model. The key lies in its regularization parameter alpha. Linearmodel CV uses cross-validation to determine the optimal alpha value, which controls the amount of regularization applied to the model. By shrinking the coefficients of less important features towards 0, linearmodel CV effectively performs feature selection, leading to a more parsimonious model. D. All of the above. Linearmodel least absolute shrinkage and selection operator is a linear model that uses regularization to shrink the coefficients of less important features towards 0. In a linear regression model predicting house prices, linearmodel might shrink the coefficients of features like number of bathrooms and garage size towards 0 if they have less impact on the price compared to features like area and location. Regularization is a technique used in machine learning to prevent overfitting by adding a penalty term to the loss function. In a linear regression model, regularization can help prevent the model from fitting the training data too closely, which can lead to poor performance on unseen data. Feature selection is the process of identifying and selecting the most relevant features from a Dataset for a given task. In a machine learning model predicting customer churn, feature selection might identify customer tenure, number of complaints, and average monthly spending as important features. Least angle regression (LAS) is an algorithm used to build a linear model by iteratively adding features based on their correlation with the target variable. LAS can be used to find the optimal set of features for predicting customer satisfaction. By adding features one at a time based on their correlation with the satisfaction score. Cross-validation is a technique used to evaluate the performance of a machine learning model by dividing the data into multiple folds and training and testing the model on different combinations of folds. To evaluate the performance of a model predicting loan defaults, cross-validation can be used to split the data into 5 folds, train the model on 4 folds, and test it on the remaining fold. The regularization parameter alpha controls the amount of regularization applied to a model. A higher alpha value will result in stronger regularization, shrinking the coefficients of less important features more aggressively. Overfitting occurs when a model learns the training data too well, resulting in poor performance on unseen data. A model predicting stock prices that overfits the training data might make inaccurate predictions on future stock prices because it has learned the specific patterns of the training data. Model interpretability refers to the ease with which a model's predictions can be understood and explained. A model that uses only a few features to make predictions is easier to interpret than a model that uses a large number of features. A parsimonious model is a model that uses as few features as possible to achieve good performance. A model that uses only area and location to predict house prices is more parsimonious than a model that uses area, location, number of bathrooms, and garage size. Lasso-LAS-CV is a class in scikit-learn that implements the Lasso-LAS-CV algorithm. To use Lasso-LAS-CV to build a model, you would first create an instance of the class and then call the fit method to train the model on your data. The fit method is used to train a machine learning model on a given dataset. To train a Lasso-LAS-CV model on a dataset containing house prices, you would call the fit method with the dataset as an argument. The predict method is used to make predictions using a trained machine learning model. To make predictions on new data using a trained Lasso-LAS-CV model, you would call the predict method with the new data as an argument. The core attribute of a Lasso-LAS-CV model stores the coefficients of the features. To get the coefficients of the features in a trained Lasso-LAS-CV model, you would access the core attribute. The alpha attribute of a Lasso-LAS-CV model stores the optimal regularization parameter alpha found by the algorithm. To get the optimal alpha value found by a Lasso-LAS-CV model, you would access the alpha attribute. Ridge regression is another type of linear model that uses regularization to prevent overfitting. But instead of shrinking coefficients to 0, it shrinks them towards 0. Ridge regression can be used to predict stock prices, and it can help prevent the model from overfitting the training data by shrinking the coefficients of less important features towards 0. Elastic net is a hybrid regularization technique that combines the L1 penalty of Lasso with the L2 penalty of ridge regression. Elastic net can be used to predict customer churn, and it can help prevent overfitting and improve model performance by combining the benefits of both Lasso and ridge regression. Principal component analysis (PCA) is a dimensionality reduction technique that transforms a dataset into a lower dimensional space by identifying the principal components, which are the directions of greatest variance in the data. PCA can be used to reduce the dimensionality of a dataset containing customer demographics, such as age, income, and education level, to identify the most important features for predicting customer behavior. Recursive feature elimination (RFE) is a feature selection technique that iteratively removes features until the desired number of features is reached. RFE can be used to select the most important features for predicting loan defaults by iteratively removing features based on their importance. Which of the following statements is true about the LaSu-Las CV estimator in scikit-learn? A. It is a regularized linear regression model that utilizes the least angle regression LAS algorithm for efficient variable selection and coefficient estimation. B. It performs cross-validation to select the optimal alpha parameter for the LaSu penalty, leading to improved generalization performance. C. It is particularly effective in handling high-dimensional datasets with many features, promoting sparsity and reducing overfitting. D. All of the above. A. It is a regularized linear regression model that utilizes the least angle regression LAS algorithm for efficient variable selection and coefficient estimation. Correct. LaSu-Las CV leverages the LAS algorithm for efficient variable selection, which progressively adds features to the model based on their correlation with the target variable. This approach helps identify the most important features, making the model more interpretable. Least angle regression LAS. LAS is a computationally efficient algorithm for finding the entire solution path of the LaSu regression. It progressively adds features to the model based on their correlation with the target variable. This approach helps in identifying the most important features and providing insights into the impact of different alpha values on the model. B. It performs cross-validation to select the optimal alpha parameter for the LaSu penalty, leading to improved generalization performance. Correct. LaSu-Las CV implements cross-validation to determine the optimal alpha parameter for the LaSu penalty. This ensures the model's robustness and generalizability to unseen data. Cross-validation. Cross-validation is a technique used to evaluate the performance of a model on unseen data. It involves splitting the data into multiple folds and using each fold as a validation set while training on the remaining folds. This helps estimate the model's generalization ability and ensures that the model is not overfitting to the training data. C. It is particularly effective in handling high-dimensional datasets with many features, promoting sparsity and reducing overfitting. Correct. LaSu-Las CV is effective for high-dimensional datasets due to its ability to promote sparsity through LaSu regularization. This reduces overfitting by shrinking the coefficients of unimportant features to zero, leading to a simpler and more accurate model. LaSu regularization. LaSu regularization adds a penalty term proportional to the absolute values of the coefficients. This penalty encourages sparsity by shrinking the coefficients of unimportant features towards zero. This results in a model with fewer non-zero coefficients, improving interpretability and efficiency. D. All of the above. Correct. All the statements A, B, and C are true regarding the LaSu-Las CV estimator. It combines the efficiency of LAS, the sparsity-inducing power of LaSu regularization, and the robustness of cross-validation. LaSu-Las CV. LaSu-Las CV is a powerful technique that combines the strengths of the least angle regression LAS algorithm and the LaSu regularization. It efficiently identifies the most important features by gradually adding predictors, reducing the complexity of the model. It also performs cross-validation to determine the optimal alpha parameter for the LaSu penalty, ensuring that the model generalizes well to unseen data. D1. Feature selection. LaSSOO-LaS CV can be used to identify the most relevant features in a high-dimensional dataset, simplifying the model and improving its interpretability. In a scenario with a large number of features, LaSSOO-LaS CV can help identify the crucial features that significantly impact the target variable. By shrinking the coefficients of less relevant features to zero, it simplifies the model and enhances its interpretability. 2. Sparse model representation. It can create sparse models by shrinking unimportant features to zero, leading to more concise and efficient models. Consider a model with numerous features, many of which might be redundant or have minimal impact on the target variable. LaSSOO-LaS CV helps create a sparse model by removing these insignificant features. This results in a more compact and computationally efficient model, simplifying the analysis without compromising accuracy. 3. Handling correlated predictors. It can handle correlated predictors by promoting sparsity and reducing the impact of redundant features, leading to more stable and reliable models. When features are highly correlated, models can become unstable and unreliable. LaSSOO-LaS CV tackles this issue by promoting sparsity, shrinking the coefficients of correlated features towards zero. This minimizes the impact of redundant features, resulting in a more stable and reliable model. 4. Predictive modeling. LaSSOO-LaS CV can be used for predictive modeling in various domains, such as finance, healthcare, and marketing, where it can achieve high accuracy with sparse models. LaSSOO-LaS CV is applicable in diverse domains, including finance predicting stock prices, healthcare predicting disease outcomes, and marketing predicting customer behavior. Its ability to create sparse models with high accuracy makes it a valuable tool for predictive modeling in these areas. 1. Regularization. LTBRGT regularization techniques are used to prevent overfitting by adding a penalty term to the loss function. The penalty discourages overly complex models with large coefficients. LTBRGT USE cases. LTBRGT1. High-dimensional datasets. Regularization helps in handling high-dimensional datasets with more features than samples, reducing overfitting and improving model generalization. LTBRGT 2. Feature selection. Regularization techniques can automatically select relevant features by shrinking the coefficients of unimportant features towards zero, leading to more interpretable models. LTBRGT 3. Improving model stability. Regularization can improve the stability of the model by reducing the influence of outliers and reducing the variance of the model's predictions. LTBRGT. Regularization, a key technique in machine learning, helps prevent overfitting by adding a penalty term to the loss function. This penalty discourages overly complex models with large coefficients, leading to better generalization to unseen data. Regularization is particularly useful for high-dimensional datasets where the number of features exceeds the number of samples. It can also be used for feature selection by shrinking the coefficients of unimportant features towards zero, resulting in more interpretable models. Additionally, regularization enhances model stability by reducing the influence of outliers and the variance of predictions. Loss function. Original loss function. Regularization penalty. The regularization penalty is added to the original loss function, penalizing large coefficients. This encourages the model to find solutions with smaller coefficients, reducing overfitting and improving model stability. 2. Lasso regularization LTBRGT Lasso regularization adds a penalty term proportional to the absolute values of the coefficients. It encourages sparsity by shrinking the coefficients of unimportant features towards 0. LTBRGT USE cases LTBRGT1. Feature selection Lasso regularization can be used for feature selection by identifying and eliminating features that are not strongly correlated with the target variable. LTBRGT2. Sparse models It helps in creating sparse models by reducing the number of non-zero coefficients, improving model interpretability and efficiency. LTBRGT3. Handling collinearity Lasso regularization can handle collinearity among features by shrinking the coefficients of correlated features towards 0, improving the stability of the model. LTBRGT. Lasso regularization, a popular technique, encourages sparsity by adding a penalty term proportional to the absolute values of the coefficients. This penalty shrinks the coefficients of unimportant features towards 0, resulting in a simpler model with fewer non-zero coefficients. This sparsity leads to improved interpretability, efficiency, and stability. Lasso regularization is particularly effective in handling collinearity among features by shrinking the coefficients of correlated features towards 0. Regularization penalty. The penalty is proportional to the sum of the absolute values of the coefficients. Is a hyperparameter that controls the strength of the regularization. Higher values result in stronger penalties and more sparsity. 3. Least angle regression LARS LTBRGT LARS is a computationally efficient algorithm for finding the entire solution path of the Lasso regression. It progressively adds features to the model based on their correlation with the target variable. LTBRGT USE cases LTBRGT1. Efficient solution path LARS efficiently calculates the solution path for the Lasso regression, providing insights into the impact of different alpha values on the model. LTBRGT2. Variable selection LARS helps in selecting the most important features by identifying those that have the highest correlation with the target variable. LTBRGT3. Sparse models LARS can be used to generate sparse models by shrinking the coefficients of less important features to 0. LTBRGT. LARS is a computationally efficient algorithm used in conjunction with Lasso regression. It progressively adds features to the model based on their correlation with the target variable, allowing for efficient identification of the most influential features. LARS provides insights into the impact of different alpha values on the model, making it a powerful tool for understanding the model's behavior at different levels of regularization. This efficiency in calculating the solution path and identifying important features makes LARS a valuable asset for feature selection and creating sparse models. LARS calculates the entire solution path for Lasso regression by progressively adding features based on their correlation with the target variable. This approach helps in efficiently identifying the features that have the strongest impact on a target variable, leading to a more efficient and informative model. 4. Cross-validation LTBRGT cross-validation is a technique used to evaluate the performance of a model on unseen data. It involves splitting the data into multiple folds and using each fold as a validation set while training on the remaining folds. This helps estimate the model's generalization ability. LTBRGT USE cases LTBRGT1. Model selection cross-validation helps in selecting the best model among different options by comparing their performance on unseen data. LTBRGT 2. Hyperparameter tuning. It is essential for tuning hyperparameters, such as the regularization parameter in lasso or the number of hidden layers in a neural network, to find the optimal values for the model. LTBRGT 3. Estimating generalization error. Cross-validation provides a more accurate estimate of the model's generalization error compared to simply training and evaluating on the same data. LTBRGT. Cross-validation is a crucial technique for evaluating the performance of a model on unseen data. It involves splitting the data into multiple folds and using each fold as a validation set while training on the remaining folds. This process helps estimate the model's generalization ability, ensuring it performs well on new data. Cross-validation is particularly useful for model selection, comparing the performance of different models on unseen data and identifying the best performing option. It is also essential for hyperparameter tuning, finding the optimal values for hyperparameters such as the regularization parameter in lasso. By using cross-validation, we obtain a more accurate estimate of the model's generalization error compared to simply training and evaluating on the same data. Which of the following statements best describes the use case of lasso-Lars IC in scikit-learn's linear model? A. Finding the best model complexity for lasso regularization by using the archaic information criterion AIC. B. Regularizing the lasso model using a combination of AIC and BIC criteria. C. Performing L1 regularization with an embedded model selection process based on AIC. D. Implementing elastic net regularization with AIC and BIC as model selection criteria. A. Finding the best model complexity for lasso regularization by using the archaic information criterion AIC. False. While lasso-Lars IC uses AIC for model complexity selection, this choice focuses solely on finding the best complexity without explicitly mentioning the L1 regularization. B. Regularizing the lasso model using a combination of AIC and BIC criteria. False. Lasso-Lars IC uses only AIC for model selection, not a combination of AIC and BIC. C. Performing L1 regularization with an embedded model selection process based on AIC. True. This choice accurately describes lasso-Lars IC's functionality. It performs L1 regularization as in lasso and incorporates AIC-based model selection within a model. D. Implementing elastic net regularization with AIC and BIC as model selection criteria. False. Lasso-Lars IC implements L1 regularization lasso, not elastic net regularization. Also, it uses AIC, not both AIC and BIC. C. Performing L1 regularization with an embedded model selection process based on AIC. Lasso regularization. L1 regularization is a technique used in linear models to prevent overfitting by shrinking the coefficients of irrelevant features towards zero. In a credit risk prediction model, lasso regularization might help identify the most important factors influencing default risk, while minimizing the influence of less relevant features. AIC is a statistical measure used for model selection. It balances the goodness of fit of a model with its complexity, penalizing models with more parameters. In a marketing campaign model, AIC could help choose between a complex model with many variables and a simpler model with fewer variables, considering both predictive accuracy and interpretability. Lasso-Lars IC is implemented in scikit-learn's linear model module. To build a model using LaSouLA's IC to predict house prices based on features like size, location, and age. In LaSou regularization, a penalty term is added to the loss function. This penalty is proportional to the sum of the absolute values of the coefficients. This encourages sparsity, where many coefficients are shrunk to zero. Loss function original loss represents the error in fitting the data. The coefficients of the linear model. The coefficients of the linear model: 5.0, 1.0, 2.0, 0.0, 3.0. 1.0, 2.0, 0.0, 3.0. Loss function 5, 0, 0.5, 1.0, 2.0, 0.0, 3.0, 8.0. You have a noisy signal that you believe is composed of a few significant components. You want to find the sparse representation of this signal using a set of atoms basis vectors. Which of the following best describes the core idea of OMP in this scenario? OMP iteratively selects atoms from the dictionary that best correlate with the residual signal, adding them to the sparse representation until the desired sparsity level is reached. OMP performs a greedy search by iteratively selecting the atom that is most orthogonal to the signal, effectively removing its contribution from the signal. OMP directly calculates the sparse representation by solving a linear system of equations using the dictionary and the signal. OMP relies on a nonlinear optimization approach to minimize the difference between the original signal and its reconstruction from the selected atoms. OMP iteratively selects atoms from the dictionary that best correlate with the residual signal, adding them to the sparse representation until the desired sparsity level is reached. True. This statement accurately describes the core idea of OMP. It iteratively selects the atom that has the highest correlation with the remaining signal residual, and adds it to the sparse representation. This process continues until the desired sparsity level is achieved. This approach is greedy because it makes the locally optimal choice at each step. Greedy algorithm, sparse representation, residual signal, dictionary of atoms. OMP performs a greedy search by iteratively selecting the atom that is most orthogonal to the signal, effectively removing its contribution from the signal. False. While OMP aims to make the selected atoms orthogonal to the residual, it does not directly select atoms that are most orthogonal to the signal. Instead, it prioritizes correlation with the residual signal, as this helps in reducing the error and finding a sparse representation. Orthogonality, residual signal. OMP directly calculates the sparse representation by solving a linear system of equations using the dictionary and the signal. False. OMP does not directly solve a linear system of equations. It's a greedy algorithm that iteratively selects atoms based on correlation with the residual signal, which is fundamentally different from solving a linear system. Direct approaches to solving linear systems are often used in other methods for sparse representation, such as basis pursuit BP. Linear system of equations, basis pursuit. OMP relies on a nonlinear optimization approach to minimize the difference between the original signal and its reconstruction from the selected atoms. False. While OMP is a nonlinear algorithm, it does not directly involve nonlinear optimization. The selection of atoms is based on a greedy strategy guided by correlations with the residual signal. Nonlinear optimization is often used in more complex methods like matching pursuit MP or basis pursuit denoising BPDN. Nonlinear optimization, matching pursuit, basis pursuit denoising. A. Representing a signal is a linear combination of a few non-zero coefficients atoms from a larger Dictionary of atoms. This is useful for efficient data storage and representation. Imagine a picture of a face. You could represent it using thousands of pixels, each with a value. However, you could also represent it using a smaller number of atoms that correspond to common facial features like eyes, nose, mouth, etc. These atoms would have coefficients representing how strongly they are present in the picture. A vector in the dictionary that represents a fundamental building block of the signal. In the face image example, each atom could be a vector representing a specific facial feature like an eye shape or a nose shape, a set of atoms that form the basis for representing the signal. The dictionary can be overcomplete, meaning it contains more atoms than the signal's dimension. The dictionary would contain a collection of these atoms representing various facial features, allowing you to combine them to represent any face. The remaining part of the signal after subtracting the contributions of the selected atoms. In the face example, the residual signal would be the difference between the original picture and the reconstructed picture using the selected atoms. This residual signal would be used to guide the selection of additional atoms in the next iteration. Extracting meaningful signals from noisy data, like in audio or image processing. This involves finding sparse representations of the signals. Imagine trying to recover a music signal from a recording with a lot of background noise. OMP could help find the sparse representation of the music signal, allowing you to filter out the noise and isolate the actual music. Feature selection and dimensionality reduction in high-dimensional data. By finding a sparse representation of the data, OMP can identify the most relevant features and reduce the number of dimensions needed for analysis. If you have a dataset with hundreds of features about customers, OMP can find a sparse representation of the data. This means it can identify a small set of the most important features that explain the variation in customer behavior. This can make it easier to build more accurate and efficient machine learning models. Analyzing medical images to identify abnormalities. OMP can help isolate relevant features in the image, making it easier to detect potential problems. In medical imaging, OMP can be used to analyze images like X-rays or MRIs. It can help find a sparse representation of the image, highlighting specific features or abnormalities that may not be easily visible in the original image. sklearn, linear model, orthogonal matching pursuit. This class provides a straightforward way to use OMP in Python. It takes the dictionary and the signal as input and returns a sparse representation of the signal. Python. From sklearn, linear model import orthogonal matching pursuit. Create an OMP object. OMP orthogonal matching pursuit n non-zero coes 5. Fit the model to the data. OMP. Fit dictionary. Signal. Get the sparse representation of the signal. Sparse representation OMP. Core. Which of the following statements are true about orthogonal matching pursuit CV? A. It performs feature selection by iteratively selecting the feature most correlated with the target variable. B. It uses cross-validation to select the optimal number of features. C. It is suitable for sparse datasets with a large number of features. D. All of the above. A. It performs feature selection by iteratively selecting the feature most correlated with the target variable. This statement is correct. Orthogonal matching pursuit CV is a greedy algorithm that iteratively selects features. At each step, it chooses the feature that has the highest correlation with the residual, the difference between the current prediction and the actual target. This process is repeated until a desired level of accuracy is achieved or a maximum number of features are selected. By prioritizing features with strong correlations, the algorithm effectively performs feature selection. True. B. It uses cross-validation to select the optimal number of features. This statement is correct. The CV in orthogonal matching pursuit CV stands for cross-validation. It is a critical component of this technique. Cross-validation is used to prevent overfitting and ensure that the selected features generalize well to unseen data. By dividing the dataset into multiple folds and training the model on different combinations of these folds, we can evaluate the performance of the model with varying numbers of features. The optimal number of features is determined by the fold that yields the best performance metric, e.g., accuracy, precision, recall. True. C. It is suitable for sparse datasets with a large number of features. This statement is correct. Orthogonal matching pursuit CV is particularly effective in dealing with sparse datasets. These datasets often have a large number of features, but most of them are irrelevant or have very little influence on the target variable. Orthogonal matching pursuit CV efficiently handles this by focusing on the most informative features, leading to improved model performance and reduced computational complexity compared to using all features. True. D. All of the above. This statement is correct. As explained above, statements A, B, and C are all accurate descriptions of orthogonal matching pursuit CV. Therefore, D is the correct answer. True. D. All of the above. LT-div style quote text align center quote EGTLTFont style quote font size 14 px quote GTLTB feature. Selection LTB GTLT font GTLTBR GTTHE process of selecting a subset of relevant features from a larger set. It improves model performance by reducing noise, increasing interpretability, and mitigating overfitting. LT font GTLT div EGT. Feature selection is a crucial pre-processing step in machine learning. It aims to identify and retain only the most relevant features that contribute significantly to the model's prediction. This process helps in several ways. Reduces noise. Irrelevant features can introduce noise and make the model learn spurious patterns, reducing its accuracy. By removing them, we improve the signal-to-noise ratio and enhance model performance. Increases interpretability. Fewer features make the model more transparent and easier to understand. This allows us to identify the key factors driving the predictions, which is valuable for decision-making and understanding the underlying relationships in the data. Mitigates overfitting. Overfitting occurs when a model learns the training data too well and fails to generalize to new data. Feature selection helps to simplify the model and reduce the risk of overfitting by removing features that contribute little to the overall prediction. LT-div style quote text align center quote EGTLTFont style quote font size 14 px quote GTLTB GTSPARSE. Datasets LTB GTLT font EGTLTBR datasets where most of the features have 0 or near 0 values. This is common in high-dimensional data like text, genomics, and images. LT font GTLT div EGT. Sparse datasets are characterized by having a large number of features, high dimensionality, but a small number of non-zero values. In these datasets, most features are irrelevant or have negligible impact on the target variable. This is common in several domains. Text data. In text analysis, a document can have a vast vocabulary features. However, most words appear rarely, leading to a sparse representation. Genomics. Genomic data often involves tens of thousands of genes features for each individual. The expression of many genes is low or absent, resulting in a sparse representation of the data. Images can be represented as matrices, where each pixel corresponds to a feature. Although images have many pixels, most are similar or represent background, leading to sparsity. Sparse datasets pose challenges for traditional machine learning algorithms, which often assume dense data. Feature selection techniques like orthogonal matching pursuit (CV) are specifically designed to efficiently handle these sparse datasets. LTDIV style quote text align center quote EGTLTFont style quote font size 14px quote GTLTBGT cross validation LTBGTLT font GTLTBRGTA resampling technique used to assess the performance of a model on unseen data. It splits the data into folds, trains on a subset, and evaluates on the remaining part, providing a more robust estimate of model performance. LT font GTLT DVGT. Cross-validation is a powerful technique used to evaluate the performance of a machine learning model and prevent overfitting. Here's how it works. 1. Splitting the data. The dataset is divided into multiple folds, typically 5 or 10. 2. Training and testing. The model is trained on a subset of the folds, e.g. 4 out of 5 folds, and evaluated on the remaining fold, the held-out fold. 3. Repeating the process. This process is repeated multiple times, each time using a different fold as the held-out set. 4. Averaging the results. The performance metrics, e.g. accuracy, precision from each fold, are averaged to provide a more robust and reliable estimate of the model's performance on unseen data. Cross-validation helps ensure that the model generalizes well and avoids fitting too closely to the training data, which can lead to poor performance on new examples. LTDIV style quote text align center quote EGTLTFont style quote font size 14px quote GTLTBGT greedy algorithm LTBGTLT font GTLTBRGTA, an algorithm that makes locally optimal choices at each step, hoping to arrive at a globally optimal solution. This can be computationally efficient but may not always find the best solution. LT font GTLT DVGT. A greedy algorithm is a problem-solving approach that makes the best decision at each step, based on the current information available, without considering the potential consequences of these choices on future steps. While this approach can be computationally efficient, it doesn't always guarantee the most optimal solution. Example: imagine you are traveling from point A to point B with multiple intermediate stops. A greedy algorithm might choose the shortest path to the next stop at each step, even if this doesn't lead to the overall shortest path to point B. It might get stuck in a local optimum and miss out on a better solution. Real-world use cases. Huffman coding. A greedy algorithm is used to build a binary tree for efficient compression. Dijkstra's algorithm. A greedy algorithm for finding the shortest path in a graph. Knapsack problem. A greedy algorithm can be used to maximize the value of items that can fit in a knapsack, given weight constraints. LTDIV style quote text align center quote EGTLTFont style quote font size 14px quote GTLTBGT image classification. LTBGTLT font GTLTBRGTS, electing relevant features from high-dimensional image datasets to improve classification accuracy. LT font GTLT DVGT. Image classification is a fundamental task in computer vision. It involves assigning a label, e.g. cat, dog, car, to an image. Feature selection plays a crucial role in image classification, especially for high-dimensional image datasets. High-dimensionality images are represented as matrices with a large number of pixels, each representing a feature. This creates high-dimensional data, making it computationally expensive and potentially leading to overfitting if all features are used directly. Relevant features. Feature selection techniques help to identify the most informative features, such as edges, shapes, textures, or color gradients, that contribute significantly to the classification task. By focusing on these relevant features, we reduce noise, simplify the model, and improve classification accuracy. LTDIV style quote text align center quote EGTLT font style quote font size 14px quote GTLTB Analysis LTB font EGTLTB art identifying important words or phrases in text data for sentiment analysis or topic modeling. LT font GTLT div Text analysis is a broad field that involves extracting insights from textual data. Feature selection is essential for many text analysis tasks, such as sentiment analysis and topic modeling. Sentiment analysis identifying the emotional tone positive, negative, neutral expressed in a piece of text. Feature selection helps to identify words or phrases that are most strongly associated with positive or negative sentiment, improving the accuracy of sentiment classification. Topic modeling discovering the underlying topics or themes present in a collection of documents. Feature selection can identify words or phrases that are highly relevant to specific topics, allowing for more accurate topic extraction and analysis. LTDIV style quote text align center quote EGTLT font style quote font size 14px quote GTLTB genomics LTB font EGTLTB art analyzing gene expression data to identify genes associated with disease. LT font GTLT div Genomics involves studying the complete set of genes and their interactions. Gene expression data, which measures the levels of gene activity, is often high-dimensional and sparse. Feature selection plays a crucial role in identifying the genes that are most relevant to disease development or progression. Disease association by selecting genes that show significant changes in expression in diseased individuals compared to healthy controls. We can gain insights into the biological pathways and genetic factors involved in the disease. Personalized medicine identifying genes associated with drug response can help develop personalized treatment strategies, tailoring therapies to individual patients based on their genetic makeup. Feature 1, Feature 2, Feature 3, Feature 4, Feature 5, Feature 6. Feature 7, Feature 8, Feature 9, Feature 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Imagine we have a dataset with 10 features feature 1 to feature 10 and a target variable representing the outcome we want to predict. We can use orthogonal matching pursuit CV to select the most relevant features. Process 1. Initialization. The algorithm starts by selecting the feature that is most correlated with a target variable, e.g., feature 3 in this example. 2. Iteration. It then calculates the residuals, the difference between the current prediction and a actual target, and identifies the feature that has the highest correlation with these residuals. 3. Feature selection. This process continues iteratively, adding one feature at a time, until a desired level of accuracy is achieved or a maximum number of features are selected. 4. Cross-validation. Throughout this process, cross-validation is employed to evaluate the model's performance with different numbers of features. By splitting the dataset into multiple folds and training the model on different combinations of these folds, we can determine the optimal number of features that generalize well to unseen data. What is the primary advantage of using ARD regression in scikit-learn for linear regression tasks? A. ARD regression automatically performs feature selection by identifying and shrinking coefficients of less informative features towards 0. B. ARD regression is significantly faster than traditional linear regression models, especially for large datasets. C. ARD regression provides a more robust solution to overfitting by adding a regularization term to the loss function. D. All of the above. A. ARD regression automatically performs feature selection by identifying and shrinking coefficients of less informative features towards 0. Correct ARD regression incorporates automatic relevance determination (ARD), which utilizes a prior distribution over coefficients. This prior encourages sparsity, effectively shrinking coefficients of less informative features towards 0. This inherent behavior contributes to feature selection, as features with insignificant coefficients become less influential in the model. Automatic relevance determination (ARD) is a technique that automatically assigns a relevance score to each feature. Features with low relevance scores are essentially ignored by the model, effectively performing feature selection. ARD is particularly effective in scenarios with a large number of features, such as gene expression analysis or image recognition. By automatically identifying and eliminating irrelevant features, ARD helps improve model accuracy and reduces computational complexity. This is because it focuses on the most significant features. Consider a dataset with 10 features. ARD might assign high relevance scores to the first 3 features and low relevance scores to the rest. During model training, the coefficients of the less relevant features will be shrunk towards 0, effectively reducing their influence on the final prediction. B. ARD regression is significantly faster than traditional linear regression models, especially for large datasets. Correct. While ARD regression might not be significantly faster than traditional linear regression models in all cases, it can be beneficial for large datasets. The reason is that ARD's feature selection capabilities can reduce the computational burden associated with handling many features. However, the speed advantage is not the primary benefit of ARD regression, as other factors contribute to performance gains, such as reducing overfitting and improving generalization. Computational efficiency. ARD regression can improve computational efficiency, especially when dealing with high-dimensional data. By automatically identifying and removing irrelevant features, ARD can simplify the model and make computations faster. It also reduces the training time. In large-scale machine learning applications, such as image recognition, where datasets often contain millions of features, ARD can significantly speed up the model training process. Suppose a dataset has 100 features. If ARD regression can identify and shrink the coefficients of 50 features towards 0, the model effectively reduces the number of parameters by 50. This can result in faster training times and a more manageable model. C. ARD regression provides a more robust solution to overfitting by adding a regularization term to the loss function. Correct ARD regression uses a Bayesian approach and effectively adds a regularization term similar to L1 regularization to the loss function. This regularization term helps prevent overfitting by penalizing complex models and encouraging simpler models that generalize better to unseen data. The regularization term helps to control the complexity of the model. Regularization is a technique that helps prevent overfitting by adding a penalty term to the loss function. The penalty term discourages complex models and encourages models that generalize better to unseen Data regularization is commonly used in machine learning to improve the performance of models, especially when dealing with noisy data or high-dimensional datasets. The model is penalized based on the complexity. This ensures that the model generalizes well, without overfitting. Let's say the loss function for a linear regression model without regularization is the sum of squared errors. Adding a regularization term, such as L1 or L2, will penalize large coefficient values, effectively reducing the model's complexity. This penalization term reduces overfitting. D. All of the above. Correct ARD regression offers all the benefits mentioned in the previous choices. It automatically performs feature selection by shrinking coefficients of less informative features towards zero, contributing to improved computational efficiency, especially for large datasets. It also provides a robust solution to overfitting by adding a regularization term to the loss function. D. All of the above. Which of the following statements are true about the scikit-learn Bayesian ridge model? A. It implements Bayesian linear regression with an L2 regularizer. B. It uses a prior distribution over the weights to avoid overfitting. C. It can handle missing data through imputation. D. It's particularly well suited for datasets with high dimensionality. A. All of the above. Correct. This statement is accurate. The Bayesian ridge model combines the principles of Bayesian linear regression, which incorporates prior knowledge into the model, with L2 regularization, which penalizes large weights to prevent overfitting. The Bayesian ridge model combines the strengths of Bayesian linear regression with L2 regularization. Correct. Bayesian linear regression, a key component of Bayesian ridge, utilizes prior distributions over the model weights. These priors guide the learning process and help prevent overfitting by introducing a form of regularization. Bayesian linear regression incorporates prior knowledge about the model's parameters through a prior distribution. Correct. The Bayesian ridge model supports imputation, a technique for filling in missing data values. It estimates the missing values based on the available data, making it suitable for datasets with missing values. The model also supports imputation, allowing it to handle missing data by estimating the missing values based on the available data. Correct. Bayesian ridge is well suited for high-dimensional datasets because its regularization capabilities help prevent overfitting in such scenarios. The L2 regularization shrinks the weights, effectively controlling the complexity of the model. Furthermore, Bayesian ridge excels in high-dimensional datasets, as it can effectively regularize the model to prevent overfitting in such scenarios. Correct. All the previous statements AD are true about the Bayesian ridge model. Therefore, option A is the correct answer. In summary, the Bayesian ridge model offers a powerful approach for regression problems, combining the benefits of Bayesian inference and regularization for improved performance and robustness. A. All of the above. Bayesian linear regression incorporates prior knowledge about model parameters using probability distributions. This prior knowledge guides the learning process, leading to more robust and less overfitted models. Imagine you are trying to predict house prices. You know that the size of a house is a strong predictor. Using a Bayesian linear regression model, you can incorporate this prior belief by assigning a prior distribution to the coefficient of a size variable. This prior distribution would reflect your confidence that size influences price, predicting customer churn, estimating the probability of loan defaults, analyzing medical data to predict disease risk. Regularization L2, a technique for preventing overfitting in machine learning models by adding a penalty term to the loss function. This penalty term discourages the model from assigning large weights to features, leading to simpler and more generalized models. Consider a linear regression model where you have many features, some of which might be irrelevant. Using L2 regularization, you introduce a penalty proportional to the square of the weights. This penalty encourages the model to shrink the weights of less important features towards zero, effectively reducing the influence of those features on the model's predictions. Predicting stock prices, building recommendation systems, image classification tasks, prior distribution. In Bayesian statistics, a prior distribution represents our beliefs about the values of model parameters before observing any data. It allows us to incorporate prior knowledge into the model. Suppose you are building a model to predict the number of customers visiting a store on a given day. You might have a prior belief that the average number of customers is around 50. You can represent this belief using a prior distribution, such as a normal distribution centered at 50. Medical diagnosis, spam filtering, natural language processing, overfitting, a situation where a machine learning model performs well on the training data but poorly on unseen data. This occurs when the model has learned the training data too well, including its noise and outliers, making it unable to generalize to new data. Imagine you are training a model to classify images of cats and dogs. If the model overfits, it might perfectly classify the images in your training set but struggle with new images. This happens because the model might have learned specific features from the training images that are not representative of cats and dogs in general. Image classification, speech recognition, machine translation, imputation, a technique for filling in missing data values in a dataset. It uses available data points to estimate the missing values. Imagine you are analyzing customer data and some entries are missing ages. Imputation can be used to fill in those missing ages based on the age values of other customers with similar characteristics. Customer segmentation, fraud detection, predictive maintenance, high dimensionality, a situation in machine learning where the number of features columns in a dataset is significantly larger than the number of data points rows. High dimensionality can make it difficult for models to learn effectively. Consider a dataset of medical records where each patient has thousands of features, including gene expressions, medical history, and lifestyle factors. This dataset is high dimensional because the number of features is much larger than the number of patients. Genomics research, drug discovery, financial modeling, predicting continuous target variables, for instance, predicting house prices based on features like location, size, and number of bedrooms, handling datasets with a large number of features, for example, analyzing gene expression data in genomics research to identify disease biomarkers. When robustness to outliers is desired in situations where outliers can significantly influence model predictions, Bayesian Rich can provide a more stable solution. What are the key strengths of using the sklearn, linear model, multitask elastic net model for machine learning tasks? A. It effectively handles high-dimensional datasets, reducing the risk of overfitting. B. It can simultaneously learn multiple related targets, improving efficiency and performance. C. It combines L1 and L2 regularization, promoting sparsity and stability in the model. D. All of the above. A. It effectively handles high-dimensional datasets, reducing the risk of overfitting. True. The multitask elastic net model, due to its L1 and L2 regularization, promotes sparsity and stability, effectively handling high-dimensional datasets. by driving irrelevant features coefficients towards zero. The model prevents overfitting, which occurs when a model learns the training data too well, leading to poor generalization on unseen data. B. It can simultaneously learn multiple related targets, improving efficiency and performance. True. The multitask elastic net is designed for multitask learning, enabling the model to simultaneously learn multiple related targets, leading to improved efficiency and performance. This is achieved by leveraging shared information between the tasks and reducing redundancy in a learning process. C. It combines L1 and L2 regularization, promoting sparsity and stability in the model. True. The multitask elastic net model uses elastic net regularization, which is a blend of L1 lasso and L2 ridge regularization. L1 regularization, also known as lasso, encourages sparsity by driving some coefficients towards zero, simplifying the model and potentially improving interpretability. L2 regularization, also known as ridge, adds a penalty proportional to the squared magnitude of the coefficients, improving stability and preventing overfitting in high-dimensional data. D. All of the above. True. As all the above choices are true, the correct answer is D. The multitask elastic net model combines the advantages of handling high-dimensional data, learning multiple tasks simultaneously, and promoting sparsity and stability. D. All of the above. L1 regularization lasso encourages sparsity by driving some coefficients to zero, simplifying the model and potentially improving interpretability. Imagine predicting house prices based on various features like size, location, number of bedrooms, etc. Lasso might identify number of bathrooms as a less significant feature and drive its coefficient close to zero, effectively eliminating it from the model, resulting in a simpler and more interpretable model. L2 regularization ridge adds a penalty proportional to the squared magnitude of the coefficients, improving stability and preventing overfitting in high-dimensional data. Consider predicting student performance based on exam scores, attendance, and project grades. If there are many features with high correlations, e.g., two different exams in the same subject, ridge regularization prevents the model from relying heavily on any single feature, leading to a more balanced and stable prediction. Elastic net regularization combines L1 and L2 regularization, leveraging the strengths of both approaches for a balanced model that is both sparse and stable. Predicting customer churn based on factors like usage patterns, demographics, and customer service interactions. Elastic net might reduce the impact of less impactful features L1 while also ensuring stability by controlling the overall influence of features with high correlation L2. Multitask learning multiple related tasks simultaneously, allowing the model to leverage shared information and improve performance across all tasks. In a medical context, predicting multiple health outcomes like blood pressure, cholesterol levels, and heart rate for a patient using shared medical history and lab test results. By training a model on all three targets simultaneously, it can learn valuable relationships between them, improving the accuracy of each prediction. sklearn, linear model, multitask elastic net LTBRGT, a linear model that combines L1 and L2 regularization to handle multiple related target variables, effectively addressing high-dimensional data and promoting sparsity and stability. A company wants to personalize product recommendations for customers based on their purchase history, browsing activity, and demographic information. Multitask elastic net can be used to learn multiple related tasks simultaneously, predicting product relevance, predicting purchase likelihood, and predicting customer satisfaction. By considering these tasks together, the model can leverage shared information and provide more accurate and personalized recommendations. Multi-label classification, predicting multiple labels for a given instance, like classifying images into multiple categories. Time series forecasting, predicting multiple time series variables simultaneously, like forecasting sales, demand, and inventory levels. Biomedical data analysis, modeling multiple biological markers to predict patient outcomes or disease progression. Recommendation systems, personalizing recommendations based on multiple user preferences and item attributes. What is the key functionality of sklearn's multitask elastic net CV? Multitask elastic net with cross-validation. A. Performs L1 and L2 regularization to minimize the cost function for a single target variable. B. Fits a linear model with elastic net regularization to multiple target variables simultaneously. C. Finds the best hyperparameters for a linear regression model with cross-validation. D. All of the above. A. Performs L1 and L2 regularization to minimize the cost function for a single target variable. False. While multitask elastic net CV uses L1 and L2 regularization, it's specifically designed for multi-target regression problems, meaning it handles multiple target variables simultaneously, not a single one. B. Fits a linear model with elastic net regularization to multiple target variables simultaneously. True. This is the core functionality of multitask elastic net CV. It uses elastic net regularization, combining L1 and L2 penalties to fit a linear model with multiple output variables targets at once. C. Finds the best hyperparameters for a linear regression model with cross-validation. True. The CV in multitask elastic net CV stands for cross-validation, which is used for hyperparameter tuning like regularization strength and L1 ratio for the multi-target regression model. D. All of the above. True. Multitask elastic net CV combines all the features mentioned in choices A, B, and C. It uses L1 and L2 regularization, fits a linear model to multiple targets, and optimizes hyperparameters using cross-validation. D. All of the above. Multi-target regression. A type of regression where the model predicts multiple output variables targets simultaneously. Unlike traditional regression, which focuses on a single target. Real-time use cases. Predicting price and demand of a product based on various features like its characteristics, market trends, and historical sales data. Forecasting multiple economic indicators, such as inflation, unemployment, and GDP growth, based on economic factors. Elastic net regularization, a regularization technique that combines both L1 lasso and L2 ridge penalties. It allows for feature selection like lasso while preventing overfitting like ridge. Real-time use cases. Predicting customer churn by considering factors like customer demographics, usage patterns, and billing history. The regularization helps identify the most influential factors. Building a model to predict housing prices using features like location, size, number of bedrooms, and amenities. The regularization can identify the most relevant features and prevent overfitting to noisy data. L1 regularization lasso, a regularization technique that adds a penalty to the model's coefficients proportional to their absolute values. This encourages sparsity in the model, meaning it sets some coefficients to 0, effectively performing feature selection. Real-time use cases. Identifying the most influential factors affecting a customer's propensity to purchase a product. Detecting important variables in a healthcare dataset for predicting the risk of a disease. L2 Regularization Ridge. A regularization technique that adds a penalty to the model's coefficients proportional to their squared values. This prevents the coefficients from becoming too large, thereby reducing overfitting and improving model generalization. Real-time use cases. Building a model to predict stock prices based on various financial indicators. The regularization helps avoid overfitting to historical stock data and improves the model's ability to predict future prices. Predicting loan default rates based on borrower's credit score, income, and debt-to-income ratio. The regularization prevents overfitting to outliers in the dataset, making the model more reliable. Cross-validation. A technique used to estimate the performance of a model on unseen data. It involves splitting the data into multiple folds and training the model on different combinations of folds to evaluate its performance. Real-time use cases. Evaluating the effectiveness of a marketing campaign before deploying it to the entire customer base. Assessing the accuracy of a medical diagnosis model before it's used on patients. Hyperparameter tuning. The process of finding the optimal values for hyperparameters of a model. Hyperparameters are parameters that are not learned by the model but are set before training. Real-time use cases. Optimizing the learning rate and number of layers in a neural network for image classification. Adjusting the regularization strength C and kernel parameter gamma in a support vector machine SVM. For text classification. What is the primary purpose of the multitask lasso model in scikit-learn? Performing regularization for a single target variable. Simultaneously learning multiple target variables with shared feature weights. Handling categorical features in a linear regression model. Performing dimensionality reduction by selecting relevant features. All of the above. This is incorrect. While lasso regularization is used for single target variables, multitask lasso specifically handles multiple target variables. Lasso regularization. This is the correct answer. Multitask lasso is designed to learn multiple target variables simultaneously by sharing feature weights across tasks, which can improve efficiency and performance. Multitask learning. This is incorrect. Handling categorical features is typically done using techniques like one-hot encoding or dummy variables. Multitask lasso is not specifically designed for this purpose. Now, this is incorrect. While lasso regularization can contribute to feature selection, its primary focus is on reducing model complexity by shrinking less relevant coefficients. Dimensionality reduction techniques like PCA are more explicitly designed for feature selection. Now, this is incorrect because only option B is the primary purpose of multitask lasso. Now, B. Simultaneously learning multiple target variables with shared feature weights. Training a single model to predict multiple target variables simultaneously. Leveraging shared information across tasks. Example: predicting different types of medical diagnosis based on patient data. This can involve predicting multiple diseases or conditions, e.g., diabetes, heart disease, cancer based on the patient's medical history, symptoms, and test results. By learning the relationships between features and multiple outputs, multitask lasso can potentially improve accuracy and efficiency compared to separate models for each target variable. Suppose we have a dataset with features like age, blood pressure, cholesterol level, and a target variable for predicting the risk of heart disease 0 or 1. Instead of having separate models for different diagnoses, e.g., heart disease, stroke, We can train a multitask lasso model to predict the risk of multiple diagnoses simultaneously, potentially finding common factors across different diseases. A type of regularization that adds a penalty term proportional to the absolute value of the model. Coefficients. Shrinking less relevant coefficients towards zero. Example in predicting house prices. Lasso regularization can help determine which features, e.g., square footage, number of bedrooms, location are most influential and reduce the impact of less relevant features. It can also help prevent overfitting. In a linear regression model for house prices, the coefficients represent the impact of each feature on price. Lasso adds a penalty to the sum of absolute values of the coefficients. This encourages some coefficients to become zero, effectively removing those features from the model. A scikit-learn implementation of multitask lasso, combining the benefits of multitask learning and lasso regularization. Example using a model trained on a large dataset of images to predict multiple attributes, e.g., object type, color, size in a new image dataset. Multitask lasso can learn shared patterns between these attributes, potentially improving performance. Imagine a dataset where each row represents an image, and each column represents a feature, e.g., pixel values. Multitask lasso can predict multiple outputs, e.g., object type, color, size for each image by sharing feature weights across these tasks. You are working on a project to predict multiple target variables: sales, customer satisfaction, and marketing effectiveness using a single dataset. Which scikit-learn model would be most suitable for this task? Given that you want to enforce sparsity in the feature weights and perform cross-validation for optimal regularization parameter selection. A. Linear regression. A. Linear regression. False. Linear regression doesn't incorporate regularization or cross-validation. It's suitable for basic linear relationships but not for sparse feature selection or finding optimal regularization parameters. B. Lasso. B. Lasso. False. Lasso applies L1 regularization for feature selection but handles only one target variable at a time. It doesn't support multitask learning and cross-validation. C. Multitask lasso. C. Multitask lasso. False. Multitask lasso handles multiple target variables and uses L1 regularization for sparsity. However, it doesn't include cross-validation for optimal regularization parameter selection. D. Multitask lasso CV. D. Multitask lasso CV. True. Multitask lasso CV is the best choice because it handles multiple targets, applies L1 regularization to achieve sparsity, and automatically selects the optimal regularization strength through cross-validation. D. Multitask lasso CV. Multitask learning. Multitask learning. Training a model to predict multiple related target variables simultaneously. This leverages the shared information across tasks for improved performance. For example, predicting sales, customer satisfaction, and marketing effectiveness on the same data. L1 regularization lasso. L1 regularization lasso. Adding a penalty term to the loss function that encourages sparsity in the model's weights. This means some features are assigned zero weights, effectively selecting the most important features and reducing model complexity. Used for feature selection and enhancing interpretability. Cross-validation CV. Cross-validation CV. A technique for evaluating the performance of a model on unseen data. The data is split into multiple folds, and the model is trained on different combinations of folds while testing on the remaining fold. This helps in selecting the best hyperparameters like regularization strength for the model. Multitask lasso CV. Multitask lasso CV combines the benefits of multitask learning with the power of lasso and cross-validation. It's designed for situations where you have multiple related targets and want to achieve sparsity in the features while finding the best regularization parameter. For example, a medical study predicting multiple disease outcomes from patient data. Which of the following statements iterate true about scikit-learn's Huber regressor? A. Huber regressor is a robust linear regression model designed to be resistant to outliers. B. It combines the best of both worlds, the efficiency of least squares for inliers and the robustness of least absolute deviations for outliers. C. It uses a loss function that is less sensitive to outliers compared to the squared loss used in ordinary least squares OLS. D. All of the above. This statement is correct. Huber regressor is indeed a robust linear regression model, specifically designed to handle outliers effectively. It achieves this by using the Huber loss function, which is less sensitive to outliers than traditional least squares. A. Huber regressor is a robust linear regression model designed to be resistant to outliers. This statement is also correct. The Huber loss function essentially combines the efficiency of squared loss for inliers data points close to the predicted values with the robustness of absolute loss for outliers data points far from the predicted values. This balance makes Huber regressor a good choice for scenarios with potential outliers. B. It combines the best of both worlds, the efficiency of least squares for inliers and the robustness of least absolute deviations for outliers. This statement is correct. The Huber loss function is less sensitive to outliers than the squared loss used in ordinary least squares OLS. This is because the Huber loss function penalizes large errors less harshly, effectively reducing the impact of outliers on model parameters. C. It uses a loss function that is less sensitive to outliers compared to the squared loss used in ordinary least squares OLS. This statement is correct as all the previous statements A, B, and C are true about Huber regressor. D. All of the above. D. All of the above. Robust linear regression is a type of linear regression that is less sensitive to outliers in A data. It aims to provide more reliable predictions, even in the presence of extreme data points. Unlike traditional linear regression methods like OLS, which can be heavily influenced by outliers, robust regression techniques use loss functions that are less sensitive to these extreme values. Financial modeling. Robust regression can be used to handle outliers in stock prices, economic indicators, or other financial data. It can help to avoid skewed predictions due to unusual market fluctuations. Healthcare data analysis. In healthcare, robust regression can be useful for analyzing medical measurements such as blood pressure, heart rate, or other physiological data. It can help to mitigate the influence of outliers that might arise from measurement errors or unusual patient conditions. Sensor data processing. When working with data from sensors, robust regression can be employed to handle noisy readings or outliers caused by sensor malfunctions or environmental factors. The Huber loss function is a key component of Huber regressor. It combines the best features of squared loss and absolute loss for inliers data points close to the model's predictions. It uses squared loss, which encourages the model to fit these points well, for outliers data points far from the predictions. It uses absolute loss, which penalizes these points less severely than squared loss, mitigating their influence on the model. This balance between squared loss and absolute loss makes the Huber loss function robust to outliers. Huber regressor with the Huber loss function is frequently used in real-world applications to handle outliers and make models more robust. Outliers are data points that are significantly different from other data points in a dataset. They can be caused by errors in data collection, unusual events, or simply natural variations in the data. Outliers can have a significant impact on statistical analysis, especially in linear regression, as they can distort the model's parameters, leading to inaccurate predictions. Imagine you have a dataset of heights of students in a class. Most students are between 55 and 60. However, one student is 70. This student's height is an outlier, significantly taller than the rest in a simple average calculation. This outlier could skew the average height of the class, making it appear taller than it actually is. Loss functions are a key component of machine learning models. They quantify how well a model is performing based on its predictions. The goal of the model is to minimize this loss function. Different loss functions are used for different tasks and have different properties. For example, squared loss used in ordinary least squares is very sensitive to outliers. Absolute loss is less sensitive to outliers but might not fit the inliers as well. Loss functions are crucial for training and evaluating machine learning models across various domains such as image classification, natural language processing, and time series analysis. They guide the optimization process, helping the model learn patterns and make accurate predictions. Least squares is a standard method for linear regression. It minimizes the sum of the squared errors between the actual values and the predicted values. This method is efficient for inliers but is highly sensitive to outliers, which can heavily influence the model's parameters. In linear regression, the least squares method aims to find the line of best fit that minimizes the sum of squared differences between the actual values y and the predicted values for each data point. It is a commonly used method, but its sensitivity to outliers can be a disadvantage in certain scenarios. Least absolute deviations (LAD) is a robust alternative to least squares in linear regression. Instead of minimizing the sum of squared errors, it minimizes the sum of absolute errors. This approach is less sensitive to outliers because it penalizes large errors less harshly than squared loss. Unlike least squares, LAD focuses on minimizing the sum of absolute differences between actual values y and predicted values. This approach is less influenced by outliers, making it more robust for data with extreme values. Robustness in machine learning refers to the ability of a model to perform well even in the presence of noisy or outlier data. A robust model is less likely to be heavily influenced by extreme values or data errors, leading to more reliable predictions. Robust models are highly desirable in various applications where data quality might be compromised. For instance, in medical diagnostics, robust models can handle outliers in patient data, leading to more reliable disease diagnosis. Similarly, in financial modeling, robust models can handle unpredictable market fluctuations, resulting in more reliable investment strategies. Linear regression is a statistical method used to model the relationship between a dependent variable y and one or more independent variables x. It aims to find a linear equation that best fits the data, allowing for predictions of the dependent variable based on the independent variables. Sales forecasting, predicting future sales based on historical sales data, advertising expenditure, and other relevant factors. Price prediction, estimating the price of a product or service based on its features, market conditions, and similar products. Market research, analyzing the relationship between product features and consumer preferences to Identify trends and optimize marketing strategies. Ordinary least squares (OLS) is a common method for linear regression. It aims to find the line of best fit that minimizes the sum of squared errors between the actual values y and the predicted values for each data point. While efficient, OLS is very sensitive to outliers, which can significantly distort the model's parameters. OLS is a widely used method for linear regression in various fields. However, its sensitivity to outliers makes it less suitable for datasets that might contain extreme values. In such cases, robust regression techniques like Huber regressor are preferred. Which of the following statements accurately describe quantile regressor in scikit-learn? It predicts the conditional mean of the target variable based on the input features. It allows for estimating the conditional quantiles of the target variable. It can be used to model the relationship between input features and the distribution of the target variable. All of the above. This is partially true. While quantile regressor can predict the conditional mean, it's not its primary function. Its strength lies in estimating the distribution of the target, not just its average. Partially correct. This is the core functionality of quantile regressor. It enables you to predict the values of the target variable that correspond to specific quantiles, e.g., the 25th percentile, 50th percentile median, 75th percentile based on the input features. Correct. Absolutely. Quantile regressor goes beyond just predicting a single point, the mean, and helps you understand how the entire distribution of the target changes based on different combinations of input features. Correct. As explained above, quantile regressor is capable of everything mentioned in A, B, and C. It can predict the mean, estimate conditional quantiles, and model the relationship between features and the target's distribution. Correct. D. All of the above. Quantiles divide a dataset into specific proportions. Imagine you have a list of 100 numbers. The 0.5 quantile median represents the middle value, splitting the dataset into two halves. Similarly, the 0.25 quantile represents the point where 25 of the data lies below it. In sales data, the 0.9 quantile could indicate the sales volume exceeded by only 10 of the products, helping identify top-performing products. Conditional quantiles are specific quantiles of the target variable for different combinations of input features. In other words, instead of just the overall median, you can calculate the median income for people with specific education levels and job experience. Predicting the 90th percentile of electricity demand in a city based on temperature and time of day, allowing for better power grid management. Linear regression finds a linear relationship between features and the target variable. It's a basic model that aims to predict the average mean value of the target based on the input features. Predicting house prices based on factors like size, location, and number of bedrooms. The Python code snippet showcases how to create a quantile regressor model in scikit-learn. It first generates a regression dataset using make regression and splits the data into training and testing sets. Then, it creates an instance of quantile regressor, setting the quantile parameter to 0.5 for the median. It fits the model on the training data and uses it to make predictions on the test data. A data scientist uses this code to build a model that predicts the median price of used cars based on features like make, model, year, and mileage. Which of the following statements accurately describes the ransack regressor in scikit-learn sklearn? It is a robust linear regression estimator that handles outliers by randomly sampling subsets of data to fit a model and then selecting the model with the highest consensus. It is a linear regression estimator that uses L1 regularization to handle outliers. It is a linear regression estimator that uses L2 regularization to handle outliers. It is a linear regression estimator that uses a combination of L1 and L2 regularization to handle outliers. This statement is correct. RANSAC regressor uses the random sample consensus (RANSAC) algorithm, which involves repeatedly selecting random subsets of data, fitting a model to each subset, and then choosing the model that fits the largest number of data points, the consensus. Outliers are less likely to be included in these random subsets, making the resulting model robust to their influence. It is a robust linear regression estimator that handles outliers by randomly sampling subsets of data to fit a model and then selecting the model with the highest consensus. This statement is incorrect. L1 regularization lasso is primarily used for feature selection and can shrink some coefficients to 0, but it doesn't directly address outliers in the same way RANSAC regressor does. It focuses on reducing the impact of irrelevant features, not necessarily dealing with outliers directly. It is a linear regression estimator that uses L1 regularization to handle outliers. This statement is incorrect. L2 regularization ridge aims to prevent overfitting by shrinking the coefficients towards 0 but doesn't explicitly handle outliers. It's better at stabilizing the model by reducing the influence of large coefficients, which might arise due to highly correlated features, but not directly due to outliers. It is a linear regression estimator that uses L2 regularization to handle outliers. This statement is incorrect. While a combination of L1 and L2 regularization elastic net is used for feature selection and model stability, it doesn't specifically target outliers. It provides a balance between the benefits of lasso and ridge but doesn't address outliers in a way RANSAC regressor does. It is a linear regression estimator that uses a combination of L1 and L2 regularization to handle outliers. Outliers. Data points that deviate significantly from the general trend of the data. They can distort statistical calculations and model performance. In a dataset of house prices, a single house priced at 1 million in a neighborhood where most houses are priced around 500,000 would be an outlier. Robust regression. Regression methods that are resistant to the influence of outliers. They aim to minimize the impact of outliers on the fitted model. RANSAC regressor, Thiel-Sein regression, and Huber regression are examples of robust regression techniques. RANSAC random sample consensus, an iterative method for outlier rejection in data fitting. It randomly samples subsets of data, fits a model to each subset, and then chooses the model that fits the largest number of data points, effectively rejecting outliers. In image stitching, RANSAC is used to estimate the homography matrix that aligns two images, even if some feature correspondences are incorrect due to outliers. Linear regression, a statistical method used to predict a continuous dependent variable based on one or more independent variables. It aims to find a linear relationship between the variables, predicting house prices based on factors like size, location, and number of bedrooms using a linear regression model. Image stitching, estimating homography matrices in the presence of mismatched features due to outliers. RANSAC helps identify and discard these mismatches, resulting in accurate image stitching. Stitching multiple photos taken from slightly different angles to create a panoramic image. Object detection. Fitting bounding boxes to objects in images. Even when some features are corrupted or noisy, Ransack can handle outliers in the feature points used for object detection. Detecting cars, pedestrians, and other objects in a street scene. Motion tracking. Estimating trajectories of moving objects in video sequences, where outliers may be present due to occlusions or sensor noise. Ransack helps filter out these outliers, resulting in more accurate motion tracking. Tracking the movement of a person's hands in a video for gesture recognition. Financial modeling. Predicting financial trends where outlier data points can significantly skew the model's performance. Ransack can help mitigate the impact of outlier data points in financial modeling. Predicting stock prices or analyzing market trends. Which of the following statements accurately describes the Thiel-Sein regression algorithm in scikit-learn sklearn, linear model, Thiel-Sein regressor? It is a linear regression model that is highly susceptible to outliers. It is a robust regression model that is highly resistant to outliers, making it suitable for data with potential errors. It is a non-parametric regression model that does not rely on any assumptions about a distribution of data. All of the above. It is a linear regression model that is highly susceptible to outliers. False. This statement is incorrect. Thiel-Sein regression is known for its robustness to outliers, meaning it is less affected by extreme values in the data. The algorithm is designed to mitigate the impact of outliers on the regression line. It is a robust regression model that is highly resistant to outliers, making it suitable for data with potential errors. True. This statement is accurate. Thiel-Sein regression is a robust regression technique, meaning it is less influenced by outliers compared to traditional linear regression. This makes it particularly useful for datasets that might contain errors or inaccurate data points. The algorithm achieves this robustness by computing the median slope across various data points, effectively reducing the influence of outliers. It is a non-parametric regression model that does not rely on any assumptions about a distribution of data. True. This statement is correct. Thiel-Sein regression is a non-parametric method, meaning it doesn't rely on assumptions about the distribution of the data. Traditional linear regression often assumes a normal distribution, which can be limiting. Thiel-Sein avoids these assumptions, making it suitable for datasets with complex or unknown distributions. All of the above. True. This statement is correct. As explained above, Thiel-Sein regression is both robust to outliers and non-parametric, making it a versatile tool for various regression tasks, especially when dealing with data that might have errors or non-standard distributions. D. Thiel-Sein regression is robust to outliers, meaning it is less affected by extreme values in the data. Robustness in statistics refers to a method's ability to resist the influence of outliers or deviations from the assumed data distribution. In the case of Thiel-Sein regression, the algorithm uses the median slope, which is less sensitive to extreme values compared to methods like the ordinary least squares (OLS) approach used in standard linear regression. This makes it suitable for datasets with potential errors or inaccurate measurements. Imagine analyzing financial data where there might be a few unusual stock price spikes. A robust regression method like Thiel-Sein can help determine the overall trend without being overly influenced by these extreme fluctuations. This provides a more accurate picture of the stock's long-term behavior. Thiel-Sein regression does not make assumptions about the distribution of the data. Unlike traditional linear regression, non-parametric methods in statistics are those that do not rely on assumptions about the underlying data distribution. This contrasts with parametric methods, which typically assume a specific distribution like the normal distribution. Thielsen regression falls into the non-parametric category, making it suitable for datasets where the distribution is unknown or complex. This allows for greater flexibility in analyzing data without the constraints of specific distributional assumptions. Consider analyzing environmental data, such as rainfall patterns. The distribution of rainfall can be highly irregular and may not follow a simple normal distribution. A non-parametric approach like Thielsen can provide more accurate insights into the relationships between rainfall and other factors, like temperature, without being constrained by distributional assumptions. Thielsen regression is a type of linear regression, meaning it seeks a linear relationship between the independent and dependent variables. Linear regression is a fundamental statistical technique that aims to model the linear relationship between a dependent variable and one or more independent variables. The goal is to find the best fitting line that minimizes the difference between predicted and actual values. While Thielsen regression is a linear regression technique, its robustness and non-parametric nature distinguish it from standard linear regression methods. Imagine a retail business trying to understand the relationship between advertising expenditure and sales revenue. A linear regression model could be used to estimate the effect of advertising on sales, while a standard linear regression might be influenced by outliers in sales data. Thielsen regression could provide a more reliable estimate of the relationship, even if there were unusual peaks in sales due to seasonal factors or promotional campaigns. When dealing with datasets that might contain errors or outliers, Thielsen regression provides a more reliable fit than standard linear regression. Outliers are data points that deviate significantly from other points in a dataset. They can often be caused by errors in data collection or unusual events. Traditional linear regression is susceptible to outliers, as they can strongly influence the regression line. Thielsen regression overcomes this limitation by being less affected by extreme values, providing a more accurate representation of the relationship between variables in outlier-prone data. Its non-parametric nature makes it suitable for data that doesn't follow a normal distribution. The normal distribution Gaussian distribution is a common assumption in many statistical methods. However, real-world data often deviates from this ideal distribution. Thielsen regression, being non-parametric, does not rely on the assumption of normality. It can effectively model relationships in data with skewed distributions, making it valuable in diverse domains. Thielsen regression is often employed in financial analysis where data can be volatile and prone to outliers. Financial data often exhibits volatility and can be susceptible to extreme fluctuations. These fluctuations might be caused by events like economic shocks, political instability, or even speculation. Thielsen regression's robustness to outliers makes it well suited for financial modeling. It can help in analyzing trends in stock prices, exchange rates, and other financial indicators while minimizing the impact of unusual price movements. Its robustness makes it suitable for analyzing environmental data, which can be affected by measurement errors or natural variability. Environmental data can often be affected by measurement errors, natural variability, and other factors that can introduce outliers. Thielsen regression's ability to handle outliers makes it a valuable tool for analyzing environmental data. It can provide reliable insights into relationships between environmental variables, such as temperature, rainfall, and pollution levels, even in the presence of occasional extreme values.